Good afternoon to all of you, and welcome back to the next session. This session is again a general session. It will be dealing with techniques for remediation of contaminated soil and groundwater, and it will be given by Johan Gemoets, who has a very long experience with these remediation of contaminated soil and groundwater in the Flanders region. So as I said previously, Johan, we will have sometimes a break. I will follow the chat and interrupt you, but most of the time it's not needed. So consider of having a break when you feel comfortable with it. For the rest, I wish you very good luck with the session. And please, the floor is yours.
Okay, thank you, Christophe. Good afternoon to all of you. I'll start with a brief introduction maybe of myself. I work at FAO for 27 years now. I'm from background to research. I'm a chemist in background and an agricultural engineer. I work as an environmental technologist on behalf of the government in Flanders. I give them technical support for complicated site remediation issues. I also work on behalf of industry, where I typically do lab experiments to evaluate if certain remediation technologies are suitable for specific problems. And I also involved in a number of research projects. Nowadays, it has a lot to do with PFAS, which is perfluorinated compounds, so removing them from soil or groundwater or wastewater. So that's in general what I'm involved in. This lecture is a part of a course that I'm also teaching at the University of Antwerp. So I made a selection of slides. I don't know what your background is, or so sometimes there is some chemistry involved that I show. Now, don't feel afraid about some reactions that you see. You can always ask me for clarification, but I think the text itself is clear enough. But it's a kind of multidisciplinary topic. So please, if you feel that you need to ask a question, stop me and I'll try to answer, okay? I also know from myself that I'm speaking sometimes quickly. So yeah, let me know in the chat maybe if it goes too fast, and I'll try to slow down. Good.
Just a remark, I got from one of the interpreter that your sound is too low and there seems to be an echo. I don't have this issue. The question is your mic is maybe too far away. Is that a possibility? I don't know, because you're speaking to your computer, I guess.
Yes, indeed. Yeah.
Yeah. Just let me check to the please, the interpreter, Inina, can you just continue talking? You want to say something just to check if that's working now?
Yes, okay. Is this better?
And otherwise, do you have a headset or something that...
I can get a headset, yes.
Yeah, maybe just to be sure. Thank you. Yeah. I think that's the suggestion of Elina as well, to have the headset. That will make their job more easy.
Is this better?
I think I would believe so. I don't see any remark, but okay. If it would be any issue, I will interrupt you. So yeah, ask Johan to speak.
Yeah, okay, good. Then I guess we'll make a start with it, and if it needs to be harder, then yeah, let me know.
Okay, thank you, Johan.
Good. So just a brief overview of what we're going to discuss this afternoon. First of all, an overview of different remediation approaches, and these are some terminologies that are very common, which is in situ remediation of soil, or ex situ remediation, or containment. So these are the large families of approaches of how to deal with soil pollution. And then we'll go more in detail in different techniques that can be used. And first part is about ex situ soil remediation, which means you excavate the soil, and then once it's excavated, you treat it with a different number of techniques that are possible. That will be the first part of the lecture today. Then there will be a pause, and then we'll start with in situ and on-site remediation. And that means that you tackle the problem on the spot. So you don't excavate the soil, you leave the soil as it is, and you manipulate the soil chemistry or microbiology with different methods, which can be either using microbes, so biological approaches, or you can do it with chemistry and in chemicals, or you can use physical techniques such as heating the soil, for example. And the last part of the lecture is about containment methods. That means you don't really remove the pollution, but you keep it in place so that it cannot move away and get in touch with people or drinking water wells, for example. So we'll first start off with the general approaches that you can use. So soil remediation approaches can be divided in containment methods, which means you limit the spread of the contamination to the environment. And that way you limit the exposure to human people who live, for example, above near the pollution. So it's like shown in the picture. You have a toxic chemical, you keep it in the cage, and you don't let it move. So the alternative is that you really treat the problem, remove the problem. So you can remove the contamination by excavating it, for example. That would be ex situ. Or you can try to destroy it on the spot. So just, for example, add chemicals like oxidants and you break down the contaminants. Sometimes a combination of both is applied. Sometimes sites are so big that you can maybe treat the hotspot where it's very concentrated, very highly concentrated pollution. You can remove that part, and then the rest you can maybe try to contain it because it would be too costly or too complicated to solve the problem at this moment. So in general, these are the three approaches of how soil contamination can be tackled. So there is a number of approaches for each of them. So the first one is removing or destroying the pollution. That can be done ex situ or in situ. With ex situ, we mean that you excavate the soil, and then you have the option to clean it on the site. If you have a big site with a lot of space far away from a recycling center, then you typically do it on site. Or you can move the soil by ship, for example, like you see in the picture. You can move the soil to a dedicated soil recycling center, which is equipped with all the necessary tools to clean the soil. If you do it in situ, that means that you remediate the soil and or the groundwater on the spot. You do not excavate it, but you manipulate the soil properties by injecting chemicals, for example, or flushing the soil with water or with air or with detergents, for example. So there's a number of options which we'll discuss later on. So for the first family of ex situ soil remediation, what's the advantage of ex situ? First of all, it's relatively fast, assuming the site is not too big, but it's typically done in days or weeks or months, depending on the volume. And it's important to realize that it's very relatively easy to predict the results. If your site investigation is well done, you know where the contamination is. If you dig up the soil and you move it away, then you're rid of the problem. Of course, it's not always possible to dig. Often there is constructions above, there may be a factory and that's working, operational, that limits the access, so you cannot dig. Or the contamination can sink too deep. If you have a well-permeable soil, sometimes contamination can go to 50 or 100 meters deep even. Even in Flanders, we have cases up to 100 meters of depth. Also, when the contaminated area is very large, we think of steel works or something like that. It's typically hectares. It's very complicated and costly to excavate all of it. Then you would rather not excavate and apply in situ methods. An important thing to remember is when you excavate the soil, then you move contaminated soil, and some of those contaminants can be volatile. And then by digging a hole, you typically move the soil and agitate the soil so that those contaminants can evaporate. And that way you can maybe cause a risk also for people who live around the excavation area. And of course, when you excavate soil, you also have to move it. If you do it ex situ, so you ship it, for example, to a treatment center, which is 20, 30 miles away. That means you need to load either ships by preference, but if you don't have a canal nearby, then you do it by truck. That means that you have a lot of trucks. Typically, trucks are 20 tons each or 30 tons. So if you have to dig 3,000 cubes, that's a lot of trucking. So the in situ remediation methods, they typically have the opposite picture of ex situ. So the main advantage is you can leave the existing infrastructure in place. You can work or treat the soil while factories keep on working. You don't have so much impact on the surroundings because you don't dig. You don't have the costs for transportation of the soil to a certain location. And typically that means for large sites, in situ is usually the cheapest solution because of those reasons. There is a number of limitations. In situ remediation, it takes much more time typically than digging a hole and shipping the soil. And it's very much more difficult to control the process. You work in a black box, everything is in the soil and you cannot look in the soil. So you don't really know what you're manipulating is having its effect everywhere in the soil at the same level. And always for in situ treatments, for most of them, the soil needs to have enough permeability because you try to inject or extract something, and that means that it has to be able to move through the soil. If you have a clay soil, you cannot move chemicals or you cannot move pollutants out of it. So that's the limitation also of most in situ technologies. Is the speed okay, Christoph, or?
Yeah, I think it's good. Thank you, Johan. Yeah.
Okay. All right. So when dealing with ex situ remediation technologies, I'll go now over a number of techniques which are commonly applied. First step is, of course, excavation of the soil.
Johan,
Yeah.
sorry to interrupt you. For me, it was fine, but Elena, the interpreter, if you could speak a little slower. So
All right.
if you could diminish your speed, that would be fine. Thank you.
Okay, good. I'll try. So first step is excavation of the soil. Then once the soil has been shipped to a treatment center, for example, then you can either apply biological treatment, you use bacteria to degrade the pollutants in the soil. You can also, if you have dredged sediments from waterways, then you can apply similar techniques as for treating soil. And one of the most applied ones is lagooning of dredged sediments. Soil washing is technology which is very much used in Western Europe, and it's applicable for most of the pollutants. Then another option is thermal desorption. You heat the soil to evaporate the pollutants which are in it, so you need to have semi-volatile pollutants. A more extreme way of treating soil is incineration, but it's typically not applied very much because it's very expensive. Sometimes soil can be co-combusted, which means you mix it with cement materials to treat it in a cement oven. And last resort, if nothing of the above works, then you can landfill a soil. And typically before landfilling it, you may need to treat it with some chemicals to make it more stable. So you can apply solidification, stabilization. So each of those techniques now we will discuss in some more detail. So the first step is excavation. So you see here how it's working in practice. So there's typically a gasoline station where the contamination is excavated. You see on the back the crane that digs the hole. And typically what we have to do is always here is that you have a consultant who is present, who is monitoring. So the contractor who is digging is supervised by a consultant who makes sure that everything goes along the prescriptions. And in this case, he's in a white suit with gas protection, typically because this is gasoline, which means it contains volatile compounds like benzene, which may escape in the air. So excavation, as I said, you can predict very well as long as the guy who stands here takes samples of the bottom and the sides of the hole to make sure that the crane stops digging only when all the pollution is gone. So emission of contaminants is an issue here, which for some pollutions you have to take into account. Now, excavation, there is some limitations to it. So typically it's a simple, well-known technique. But for soil remediation, when you dig a hole, you need to take into account that you always dig with a slope, because otherwise, if you put a vertical wall, then the wall will collapse and you may get in trouble. So that you see here on the picture, you have this 45-degree slope, which means that, yeah, if this is the contaminated area, because of the slope, you always need a little bit bigger volume than or area than what is contaminated. Now, sometimes you need to really, you see there is, yeah, sometimes in the lower picture, you see the building. Sometimes the pollution is just against the building. Then you cannot use the slope of 45 degrees. Then you can use constructions that support the soil behind it so that you can really dig vertically. So once the soil is excavated, then you can choose to treat it in a treatment center, for example, or on the spot. And the most widely used method is bioremediation, which means you use bacteria, which are typically present in the soil, and you make the conditions for them very favorable so that they can degrade the contaminants by the natural means. So typically what you do is you try to provide oxygen to the soil because that's what bacteria need most, to oxidize the pollutants. Sometimes you also need nutrients like fertilizers, typical nitrogen or such a thing. And the important is that you need to keep the soil enough moisture, moisturized, not too much, not too little. That's to keep the air permeability optimal. So the air has to be able to move through the soil to feed the bacteria so that they can oxidize the contaminants. So the principle is shown in this figure here. So you basically use microbes. And you see on the picture here, the black spot is typically an oil spot in the soil. So microbes, they typically use oxygen and some nutrients like nitrogen. And then they consider the oil as food. They grow on it and they get energy from it. And the oil is broken down typically with formation of water and CO2 if you have alkanes. So you get some gases and water, which are harmless products. So that's the basic principle of remediation of petroleum, for example, with bacteria. So it's an oxidation reaction. So bacteria need the oxygen to break down the petroleum hydrocarbons. Now, typically, if you have fuel for heating houses or diesel oil in trucks and cars, these are alkanes mostly. You see here how an alkane typically looks like. It's a carbon-hydrogen chain. And one of them that occurs typically in diesel oil is C10, is decane. And the bacteria just use oxygen and they form CO2. They break it down to CO2 and water. So that's the basic principle. So you need oxygen, so you need to aerate the soil. And sometimes you need to add nitrogen or potassium fertilizer. But most important is keep enough oxygen in it. And that means that sometimes companies also add soil structure improvers, which means you add, for example, compost or mulch so that you get more, better structure of the soil so that the air can move easily through it. Sometimes people also add bacteria, but that's rarely needed for this kind of treatment of petroleum with ex situ biotreatments because most soils have the proper bacteria. But if you want, sometimes it could be that there's not enough bacteria. If the bioremediation after 2 or 3 months doesn't seem to work, then you may consider adding bacteria. For example, if you have wastewater sludge from a food company, that may be a good approach to add, or you can add compost, for example. So you need to keep the bacteria happy, which means they need enough moisture. So sometimes you need to spray water on the soil. They need to have a neutral pH. If you have an industrial soil with an extreme pH of maybe 9 or 10, let's say, or 5, or below 5, then it's good to correct the pH. But usually it's not needed because most soils are in the 5 to 8 range. So you need oxygen. Bacteria can use other oxidants. We'll come back later to that, but for typical soil treatment in a soil recycling center, it's not used.
Johan,
yes.
If I can interrupt you, because the translator asked if you could consider speaking slower or take a break once one. I know it's difficult because you're really into the topic, but if you could think about that. Thank you, Johan.
Okay, yeah.
The break isn't really needed, it's just speaking slower, if that's possible. Okay, thank you.
All right, yes. So one limitation for the bacteria may be that they cannot get in touch with the pollution, because the pollution is absorbed within the soil particles, or it's very strongly absorbed. And that's when you have some clay particles in the soil or a lot of organic matter, then it's more difficult for the bacteria to remove or take up the pollutants in their cell. So that may be a limitation why things may go slower. Sometimes can happen that you have a contaminated soil and some other contaminant that what you think is in there, and it may be toxic for the bacteria. That may be another reason why things go slower than you would normally expect. But in general, bioremediation of oil is not very difficult. It goes relatively smoothly. So it can be applied for different kinds of petroleum hydrocarbons like domestic fuel or petrol, but not for petroleum hydrocarbons with very long chains. If the carbon chain length is more than 30, then they're so insoluble in water that the bacteria cannot absorb them to metabolize them. So you need good permeability of soil, and typically a soil, when it's clay, things don't work very well because you cannot get oxygen in it and it's too difficult to mix the soil. In that case, you may try to improve the structure by adding a lot of compost, but it's still more complicated. The other things I mentioned already. So make sure that you know what's in the soil before you start treating it, that you don't have other contaminants which may be, for example, toxic for the bacteria. That may complicate the process. So this treatment is only for certain class of pollutants which can be degraded by bacteria, and this is typically mineral oil. Now, so this is all about petroleum hydrocarbons. Now, there's a slide which gives a little bit an indication of if you have bacteria that degrade contaminants in the environment, there is a big difference in speed at which they can degrade the contaminants. And it all depends on the type of pollutant. Some are easy to degrade and some are more difficult to degrade, but it's also dependent on the state of the environment, if the conditions are good for the bacteria. And these are some examples how different these rates can be, and it's expressed in half-life. That means the time needed to get half of the concentration of the starting concentration of the pollutant. So toluene is a molecule which is often found in paints, for example. If the conditions are not favorable, it needs about 700 days to be halved in concentration. If conditions are good, then it can be done in only 10 or 12 days. So you see the extremes depending on the environment conditions. But you also see compounds like PCE on the fourth line. It's a chlorinated solvent. If the conditions are difficult, then it may take 3,500 days to halve the concentration. If the conditions are good, about 200 days. You see, it's much slower than petroleum hydrocarbons like toluene or oxalanes. So it's important to understand different compounds degrade with different speeds. A little bit more information about petroleum hydrocarbons, but I think I'll skip this because I think I have too many slides. You can find it for yourself. It's a little bit more detailed which petroleum hydrocarbons break down easily and which are more difficult to degrade. So you don't only have alkanes in petroleum, you also have typically aromatic compounds, and then we think of compounds here like benzene or cyclohexane or toluene. If you have compounds like this, cyclohexane, these are compounds that break down very difficult. Benzene is much easier when oxygen is present, and toluene as well. So these are relatively easy to biodegrade. Another group of pollutants that bacteria may break down is polycyclic aromatic hydrocarbons. And these are compounds which have many of those benzene rings together. And these are complicated molecules. And the ones with 1 or 2 or 3 rings on top of the picture, bacteria can degrade them. But the more complicated molecules of 4 and 5 rings, they're very difficult for bacteria to degrade. So these are not feasible to treat with bioremediation. If you have a soil with coal tar, then you typically have compounds like benzoapyrene with 5 rings, and it's very difficult to degrade that for bacteria. But you have naphthalene with only 2 rings, and then they can do that very well. Another few methods to treat the soil. I think this picture I already discussed basically. So I just try to turn the soil by aerating it. It can be done with composting machines, but they require a lot of energy. There is other ways which are more, energy effective. One way of dealing it is very simple. With a crane, you put the soil on a pile, and every 2 weeks, for example, with the crane, you turn the soil to aerate it. Sometimes the soil has benzene compounds in it, or gasoline compounds, which are volatile. Then you get a lot of odor, and then you can do it undercover, like you see here in a covered area, such that the vapors can be captured. You see on the picture here in the green box, it's an air blower. It captures the air and it's sent to an activated carton filter, for example. So that may be one way of dealing with soil with volatile compounds. Another way that you can also do on site at the contaminated site is if you use what they call biopiles. So a biopile is just a pile of soil, and it's in this case, you see it if you look at the bottom figure in the length, you see you put the soil on a drainage bed of well-permeable sand that can drain the water that comes from the soil. Then you put a drainage pipe in it, in which you can blow air or suck air. And so if you see it in the front, then you see that you have different lines or pipes which are perforated to bring air or oxygen in the soil. And typically these pipes are then connected to a blower, which you see here, that sucks typically the air out of the soil, and it sends the air through an air filtration with activated carbon to treat volatile components that come out of it. So this is a simple way that everybody can do on the spot. Just make piles of soil, cover them with a plastic, and bring air through them with a ventilator. If you have dredged sediments, you can treat them in a similar way as soil with the help of bacteria. And this technique is called lagooning. So you see a treatment area where you see the soil is put again in those long piles, and then that allows the soil to be turned regularly to degrade petroleum, for example, by bacteria. But sediments that are dredged are different from soil. They typically have a lot of water still. So what they typically do is put them on a drainage sand bed. You see the yellow sand, which is well permeable. Under it is a plastic liner. And then the treatment is 2 phases. First, you let the soil drain and dry in the air. By turning it, you will evaporate the air. And eventually, when most of the water is gone, it becomes more permeable for oxygen, and then biodegradation will start. And that way you can treat the soil. Now, at the same time, when the water is draining out, of course, it will drain also some contaminants that ends up in the leachate, and this leachate is captured and treated. Right, so the first group was biological techniques, bacteria oxidize contaminants. Not all contaminations can be tackled by bacteria, and typically the ones which cannot be tackled, like metals, they typically are removed with soil washing. And soil washing is a technique, the name says it. You see the picture on the right, it's using water, and you suspend the soil in water, and you want to separate the soil in a number of different fractions. First, you split off the sand and the gravel from the soil. These are inert materials, and just with washing with water, you typically get clean sand and clean gravel. And that way you end up with a concentrated polluted fraction, which is typically the fine particles of the soil, like the clay fraction, but you also separate the organic particles of the soil, like little leaves or humic matter or coal particles. And so these are waste fractions, and these are typically landfilled or incinerated. And so the principle of soil washing is just separate soil in 2 fractions, one that you can reuse, sand and gravel, and another one that you landfill or incinerate. Now, the contaminants typically, it's good if they can be solubilized in water easily. Now, when they're dissolved in the water, they finally end up in the waste because it's a process that consumes water, because the fine fraction, the clay that you landfill, it typically absorbs a lot of water as well. So typically the water that you use for separating the soil is recycled in the process and eventually it ends up in the waste fraction. Sometimes you purify the water in the process when the contamination becomes too high in the recycled water so that the sand does not get clean anymore. Now, soil washing, you cannot do it for all soils because you don't want to put a lot of volume in the landfill. So typically in Flanders, we use the criterion that you need to get a recovery of at least 60% of sand and gravel that you can reuse and 40% of waste that you have to landfill or incinerate. If you have soils which are clay soils, then yeah, you cannot get sand out of it or not enough sand, and then it's not suitable, this technique. The advantage is it can be used for all contaminants, basically. So it means metals, oil, but then typically heavy oils, pHs, chlorinated solvents, even radionuclides. We at FITO did testings with uranium, and it worked very well for a facility in Belgium. Soil washing is an ex situ technique which can be done in soil recycling centers, but you can also do it on the spot. Some contractors, they have mobile soil washing installations and they can just do the job on the spot. Now, what are the techniques that are used in soil washing? First of all is separating according to size. You see the picture on the right of a screen. So you can have vibrating screens or rotating drums. They just separate the coarse from the fine fractions. And another technique which is used a lot is hydrocyclone separation. And I'll show on the next slide how it works. So this is a typical, on the left side is a picture of a hydrocyclone. So it's a conical apparatus, and the soil is being fed on the left side, on the number 1 here. And the soil enters as suspended in water as a slurry under high flow in the hydrocyclone, and it's thrown to the wall. And there is 2 openings in the cyclone. There is a bottom opening, which is big, and there is on the top a smaller opening. And so what's happening is that the heavy particles, which are sand particles, the coarse particles, they're so heavy that they go down. The light particles are taken up with the water. All the water, typically, or most of the water goes up from the top. So you have a separation on the bottom sand, which is washed and cleaned typically. And at the top, you have the clay fraction and the organic matter, which is light. So these light particles are taken up with the water that goes from the top. So that's a common technique, which is very simple to split soil in a usable sand fraction and a waste fraction to landfill. Another way of separating is by density. Soil has heavy particles and light particles. Typically, the sand is heavy, the organic matter is light. So you can use density separation to remove the organic fraction, which is typically more polluted from the sand fraction. And there is a number of techniques. You can do that with spirals, which come from the coal industry or the mining industry. You can do it with a jig table, which is like a vibrating table with water pulses that remove the light particles. Or you can send the soil in a column in which you have water flowing up, and the sand will sink in the upflowing water, and the organic matter will be taken out with the water. And the next slide gives again one of those techniques. So here see the spiral. So the principle is that you feed on the top the soil, the sand typically after the hydrocyclone, the sand which still has coal particles, for example, comes in here. And in the cyclone, you get a spiral motion, which means that the water is thrown to the outsides of the spiral. And the light particles, they will be moving at the outer side because the light, they go more with the water to the outside with the centrifugal force. While the heavy particles, which is sand, they don't fly away so far and they stick to the axis here. So at the bottom of the spiral, you get a separation of heavy particles at the center, the sand, which is cleaned, and the light particles at the outside, which is typically coal particles with, for example, polycyclic aromatic hydrocarbons. Sometimes some more sophisticated techniques are applied, like attrition scrubbing. That means you put a high energy mixer in the sand and you scrape the pollution from the sand grains to clean them. It's polishing, but it's very energy intensive and therefore not so much used. You can have froth flotation where you blow bubbles in a water soil suspension to remove pollutants. You can add acid or base, for example, to remove metals. You can add acid. You can add surfactants to remove oil, but all these things are pretty complicated, typically for the water treatment, and are not used so much. This is how a typical soil washing installation looks like. It's at a site in Antwerp of Deme. You see it starts here with the red box. You have the contaminated soil, and the soil typically goes to a screen as a first step to remove the coarse particles like the gravel. And then you see that the gravel is being sent to a washing drum that turns around to wash the final pollution from the gravel, and you get clean gravel. The sand, which is smaller than the gravel, it goes down with the pump and it goes to the hydrocyclone. And then the hydrocyclone sends away the organics, for example, in the clay particles, and the sand goes down, and it goes typically to a second hydrocyclone and a third hydrocyclone in this process. So it's always to get more and more cleaned. And sometimes you add, to clean the sand, attrition scrubbing, like I said, or you can apply flotation, for example, or you can apply an upstream column. These are all polishing techniques to clean the sand. So eventually you get clean sand, and in the whole process, the water is always recycled and returned to the beginning. So this is a fixed soil washing center. This is another picture of how it looks like in real life. So you have here here you see hydrocyclones. These are small size hydrocyclones. Here you have big hydrocyclones. So they separate the soil in sand and fine matter. Here you see the coal spirals or the metal spirals to remove coal particles from the sand. You see a flat screen here to dewater the sand. Finally, the sand has to be separated from the water. That's also known with the screen. And on the top, you see the big blue vessels. This is where the sludge goes, the fine fraction, which is very polluted, and it's settling in those settling tanks. But normally, this type of installation you can also put on the site. All right. So the previous one is soil washing used for all types of pollutions, like I said, but not for all types of soils, not for clay soils. Another treatment technique is thermal desorption. You use heat. You do not burn the pollution, but you heat it such that it evaporates. So you heat above the boiling point of the contaminant, and once it's evaporated, the gases you evacuate from the soil and you burn the contamination in the gas. So the advantage is you don't need to heat like an incineration to 1,000 degrees. It depends on the boiling point of the contamination, how much you have to heat. So it's a technique which you can use for semi-volatile pollutants such as mineral oil and heavy oils, PAHs, also PCBs, but also cyanides, pesticides, but metals, of course, not, because they're not volatile. Now, the temperature, as I said, depends on the pollution, and it goes between 450 degrees and 650 degrees, depending on the boiling point of the contaminants. This type of treatment you can do for all types of soil, not only sand, but also loam and some clay soils. It works in principle, but not for peat soil. If you have high organic matter, it may burn from itself, and that's not good. Also, these thermal treatment plants, they can be fixed installations or they can be mobile, that you can bring them to the spot. This is a picture of how it looks like. So you see you have a rotating drum, so it turns around to move the soil from the high end to the low end here. And you see a ventilator that blows air through it, so that the pollutants which are evaporated from the soil, they're carried by the air towards an incineration unit here. So this is the treatment of the gas. You incinerate the pollutants that are going in the gas phase, and then you see here the sand, which is heated, that comes out as clean sand. So that's basically the concept of a thermal treatment plant. So sometimes thermal treatment is not enough because some contaminants, they have high boiling points or they're very recalcitrant to treat. So you may heat the soil at higher temperatures for incineration, typically around 1,000 degrees, but you need a lot of energy, so it's very costly. So it cannot compete with thermal desorption, like we just said before. So you only do it when thermal desorption would not work. So sometimes they use for compounds like dioxins, which are very difficult to remove with thermal desorption. Because it's expensive, people often use a cement kiln as an option. So cement factories, they need soil can be added in small quantities to cement materials. And that way, typically in cement ovens, you have temperatures going up to 1,400 degrees. That means it will destroy all organic contaminants in the soil. And if you have metals, they can also be fixed in the cement to some extent if it's not too much. But realize the cement quality needs to be maintained, which means you can only you have a limited amount of soil that you can mix in cement. So it's not really a good solution if you have a lot of contaminated soil to treat. Now, sometimes the soil cannot be cleaned. It's too complicated. There is too much clay in it, for example, or the concentrations are too high. Then you can landfill it. That's the last option. You put it in a hole. But you can, in Flanders, not every soil can be landfilled. You can only do it when there is nothing else that works. So landfilling of contaminated soil, it always goes in what we call a class 1 landfill or in a mono landfill. It's a strictly regulated landfill which can accept chemical waste. So you cannot put it in any landfill because it may leach and then eventually to the groundwater. Before it's landfilled, sometimes you have to treat the soil so that the contamination will not leach and also that the material is solid enough so that there is stability in the landfill. Sometimes there is contaminations which are very large and one type of contamination, and we think typically of PFAS nowadays, for example, which is very recalcitrant compounds, which are a problem to put in a landfill because they don't break down with time, and in 1,000 years they will keep on leaching. And the landfills don't like that. So this type of pollution you can put in what they call a mono landfill. So it's a dedicated landfill that you make just for this pollution, and you make sure that it's really well sealed, which they call in salt cell conditions. So it's very well shielded at the bottom and the sides and well monitored. So this typical setup of a landfill, but I guess you know probably from this already from other courses, but basically you have the waste material in the landfill, and this is put in a hole that's really well sealed. So you have a compacted clay layer that's, if something leaches out of the material, it's stopped by the clay and it cannot go to the groundwater. And then within this clay layer, you still have a drainage layer from which you can evacuate whatever is leaching from the waste, and you can evacuate it and purify it. And then you typically also have some plastic liners as an extra protection. So these are, and they also have a permanent monitoring system so that they can verify the quality of the groundwater, that nothing leaches over time. So if you put a soil that's too complicated to clean in a landfill, this is the type of landfill you should use. There's a lot of text. I'm not going to read it all, but it's just for information because for you, of course, ammunition is very relevant. Huh? And there is a lot of information available also in the United States from the US Army or similar organizations where you can find information about how to deal with explosive contaminated soil. So here you see the website where you can find some information. It's from the organization FRTR in the United States. And it gives some information about how you deal with soil, for example, that has TNT and analogs. So TNT, you have to be aware in the environment, it will not be present at itself as such, but it will degrade in the environment, or it will also have impurities from the production of TNT. So you typically have a whole mixture of chemicals, nitroaromatics, which are present in the soil, which may cause explosions, typically have high concentrations of explosive. And typically what they say here is you should be careful that the contamination with these explosives is always below 10%. If the concentration is higher than 10 mass percent of the soil, then you get really explosions which are too big, which cannot be controlled and which will propagate. And what you can do if you have such a site with potentially high explosives, then you can try to blend the soil and try to bring the concentration below 10%. So by blending it, and you get a homogeneous mixture, and you may mix with some non-contaminated soil. So in that way, it's safer to handle for treatments. So if you go then to biological treatment later or thermal treatment, then you will not get those explosions anymore that you cannot control. It always also gives some information of which material you have to use. So you have to use certain metals, so for example, that are spark-free, so that they don't let explosions occur when you handle the soil. So you can find this information on this website. I don't know what the time is now, Christophe. Yeah, it's 50 minutes, so it's relatively well timed, I think. So I'll propose to give a 5 to 10 minute break. So it's now, I have 10 to 2, so maybe we can start at 2 again. First, we can take some questions, of course. So I don't know if anybody has a question so far.
Not at this moment, Johan. So I think it would be good to have now a 10 minutes break. And then we come back. And then meanwhile, I need to ask you something. So if you can just stay online, but I will ask it in Dutch. So I propose now to have a 10 minutes break. So we will see each other at 2. And this will be for you at 3 o'clock. Okay. See you. Ja, Johan, 2 vraagjes. Ik heb jou een berichtje verstuurd met de logo, want ze vragen wel of dat je de achtergrond kunt veranderen van jou. Nu, kijk eens in je inbox. Ik heb een berichtje naar jou gestuurd.
Ja, ik heb het wel gevonden, maar ik vind in de Zoom niet direct waar ik kan invoegen.
Ja, dus je ziet op je eigen scherm, hè, waar dat je jezelf ziet, zie je bovenaan rechts 3 bolletjes, normaal gezien. Als je op je eigen klikt, misschien moet je uit de presentatiemode gaan, misschien is dat het gemakkelijkste. Ja, ga maar uit de presentatiemode. Ja. En als jij nu, je ziet normaal, zie jij je eigen, of je eigen, hoe dat jij eruit ziet?
Ja, ik vind het enkel klein.
Ja, wel, maar daarboven rechts, zou normaal, als je met je muis erop gaat op je, boven rechts zie je 3 bolletjes normaal gezien op jezelf.
Ik zie 9 bolletjes, maar ja, kijk.
Ah ja, of 9 misschien, maar klik erop. Als ik erop klik, dan bij mij verstaat er ook Adjust Background and Effects.
Ik heb dat nog niet. Ik ga de andere eens aanklikken. Nee, ook niet. Ja, oké, dat zijn allemaal goed. Nee, dat zijn... Even kijken, ik kan het eens groter openen.
Ja.
Wacht, hè. Nu is hij weer... Ik kan deze... Waar zit dat? Video, audio. Die bolletjes zie ik nog niet. Ik heb weer recording, sign-in.
En anders moet je eens uit presentatiemode gaan, Johan. Misschien gaat dat helpen. Want nu zit je in presentatiemode. We zien je scherm. Hè. Misschien als je eruit gaat, dat beter gaat.
Oké.
Dan stop sharing of zo.
Heb ik nog niet. Stop sharing. Als ik die share klik, daar kan ik enkel kijken. Hè?
En er staan ergens bovenaan bij jou een stop sharing, want ik heb zelf
Nee, ik zie hem niet.
Ja. Een andere optie wat je kunt doen is even gewoon uit de meeting volledig gaan en dan terug ingaan. En dan, wanneer dat je aanmeldt, zou je normaal ook de vraag moeten krijgen. Zo ziet het eruit. En dan zouden bij background ook dat figuurtje kunnen uploaden. Ik heb dat eerst op mijn desktop. Je moet dat misschien op je desktop eerst bewaren, maar dan kun je die vinden. Dat is de
Ja.
andere optie.
Goed, ik zal even staat gaan.
Ja,
Hopelijk dat
oké.
tijd terug in. Ja,
Ja, nee, prima. Oké, Johan.
ja, sweet.
Is that email for the change in time and the topics confirmed?
Yeah. You mean the mail I sent you? Yeah, I think indeed. So the plan would be to have only then the session tomorrow in the morning and in the afternoon, which is a compilation of the difference as I was put in the mail. And then on Monday morning, there will be the rescheduling of this radiochemistry. And in the afternoon, then we will not have a session then, Monday afternoon.
Okay. So, I received only the last one. Let's discuss and.
Christoph, how are you?
I'm fine, Sergius. Yeah. I see Johan is back. Okay, Johan, this seems to work now.
Okay.
Okay. Yeah. And then, Johan, I still have another question to you, but I will continue in Dutch. Ik zie dat jij nog de oude template gebruikt hebt van de presentatie en de FAO-logo rechtsboven is weg. Ik heb je ook een figuurtje doorgestuurd met het FAO-logo. Kun jij eens kijken wat je typisch moet doen is in je presentatie als je dan, ik weet niet of je dat kent, in de dingen gaat. Dan moet je gaan kijken bij View en dan dat eens proberen ook te kijken of dat je dat er nog bovenin kunt zetten in je View. No. Dat noemt de master slider, is dat normaal, hè?
Ja, de slide master.
Ja, de slide master. Weet je wat ik bedoel?
Ja, ik heb die opengeklikt nu, maar dan...
Ja, de slide master. En dan, ik heb jou juist per e-mail een FAO-logo doorgestuurd.
Ja.
Als je dat kopieert, pak maar het linkse, en je gaat naar die slide master en je plakt dat erin, van je presentatie, en je zet die bovenaan rechts. Dan zou dat normaal moeten erin blijven, ook voor al je slides.
Ja, ik zal het zien.
Kijk eens of dat lukt.
Ja, ik probeer het.
Ja.
Dus ik plak het gewoon in er.
Ja,
rechtsboven.
rechtsboven. Ja, rechtsboven zit die normaal gezien. Kijk eens of dat lukt om die er rechtsbovenin te plakken.
Ja, hopelijk bedekt hij dan iets anders, want soms heb ik wel foto's.
Ja, Ja, nu, maar dan, als dat in de slide master zit, dan zit dat meestal achteraan. Dus als je er een foto hebt, dan zal die erboven staan, normaal gezien, Johan.
Ja, oké.
Je kunt anders een keer eens testen of dat lukt.
Ja, en dus dan even kijken. Hoe raak ik nu uit die slide master? Dus.
Dan moet je teruggaan naar view en dan normal. Helemaal links is dat bij mij.
View normal.
Normal, ja. Als je naar
Oké,
normal gaat,
staat erin, ja.
dan... Ja?
Ja,
Perfect.
het staat erin, maar enkel bij degene waar ik het gedaan heb, niet bij alle slides.
Maar heb je dat wel in de slide master? Want normaal gezien zou hij dat... ik weet niet, als je naar de eerste slide gaat of zo. Ah ja. Want ik zou denken... Slide master... Ja, daar ben ik ook niet zo onderlegd in. Maar ja, op zich. Als het niet lukt, dan hebben we nog 2-3 minuutjes. Hi Anna. Meanwhile, is it okay, the proposal of the change with the training, or you still had a question?
I'm trying to make a schedule.
Okay.
On 24th, on Monday to delete.
Except for the last topic I said for the 20th of November, that's still under discussion, Anna? So
yes, session on November 20, it's like...
under discussion, yeah. So,
under discussion.
Yeah.
Yeah, so only inside this previous schedule, I will change...
Okay.
31st morning, 31st tomorrow. So tomorrow we have... There will be like several.
So the timing will be the same tomorrow, except that there will be like a little bit because they were gathered together. It's like the same.
Do we have all the information for this, all the slides?
I understood from Gilles, who will give the course, that he is still actually preparing them. But I will remind him to send what the background information.
For the translators to see the words they should consider.
I will send him in a reminder. Yeah.
I see some question from Alexander in questions.
Okay. Johan, before starting the next session, there was a question. How is incineration or contaminated soil applied while retaining soil organic matter, humus from combusting?
It's not possible.
Okay.
Yeah, no, that's the disadvantage of incineration and also thermal desorption. Probably it will also remove most of the organic matter, and you will get eventually a kind of black sand. So you cannot do it for agricultural soil, anything that you can reuse as agricultural soil. So typically this soil, which is treated this way, is used for construction purposes on the road pavements and things like that. But yeah, it loses its organic matter.
Okay. Thank you for pointing this out. I think it's 2 o'clock, Johan. So
yes, indeed.
If that's fine with you, we start with the next part.
You don't see my presentation yet, I think, yeah?
No, you're not in presentation mode.
You see it now?
Yeah, I see it now. Yeah, perfect.
Take some time to go to presentation mode.
Yeah. Oh, great. That looks very good, Johan. Okay.
All right.
It's fine. Please continue.
I did not get the logo everywhere yet. I'll put it later on in the final slide. Sorry.
Okay. Thank you, Johan.
Good. So the previous part of the lecture was ex situ remediation technology. So now we come more to on-site and in situ, which means you don't move the soil, you do it on the spot. And so a first example of a technology that you can apply on-site is phytoremediation. The phytoremediation means that you use plants to remove contamination from soil. And plants can do this with different processes. you talk about phytoextraction, when the plant takes up the contaminant from the soil and moves it up through its stem to the leaves. So it's an extraction process, so that way you move pollutants out of the soil. Another way that plants can handle pollutions is with phytostabilization, and it means that pollutants are immobilized within the soil, so it doesn't take it up in the plant, but it fixes it in the soil. And sometimes this is done in combination with adding some chemicals to the soil to stabilize, for example, metals. If you have high concentrations of metals, they can be toxic for the plants. But if you add something to fix the metals to the soil, then the plants can grow better, and they help them to stabilize the metals in the soil again by chemical reactions that they catalyze. Plants can also take up contaminants which they evaporate to the air, and that's called phytovolatilization. It's not the best solution because you move pollution from the soil to the air, but it happens. For example, with chlorinated solvents like PCE, they can be evaporated by plants. The ideal solution would be that the plant degrades the pollution, and that's called phytodegradation. So the plants would take up the pollution within the biomass, and then they have enzymes within the plant that break down the pollution. And it has been shown that this can be done, for example, for TNT, but also for some chlorinated solvents like trichloroethene. And the final mechanism that plants use is rhizodegradation, so microbial degradation in the root zone, because plants, when they grow, they send some of their molecules that they make into the soil, and that is good for bacteria that grow there, and you get more bacteria in the root zone than anywhere else in the soil, and those bacteria degrade on the contamination. So it's shown, again, summarized on this slide. So the plants take it up from the soil, the contamination. They can degrade the contamination within the root zone, the rhizodegradation, and they take it up within the biomass, and then they can apply phytodegradation when their own enzymes degrade the contamination. They can stabilize the contaminants within the soil by compounds that they secrete. Or the plants take it up in the biomass, and for example, once a year, you harvest the biomass, which is loaded with, for example, heavy metals, and then you can remove the contamination from the site. Now, it's not that easy for all contamination. So typically with plants, you may be able to remove many pollutants from the soil, but it depends on how fast the plant can take it up, can metabolize it, for example, or how tight those contaminants are bound within the soil particles. And this gives an overview of for which contamination it may be feasible in a realistic time, because you have to be realizing that using plants is a solution that takes much time. It's not done like excavation in 3 weeks. It may take 10 years or maybe 50 years. And the graph shows here that what's the time frame that you think of. So from short time to long time, and here you see up to 60 years or more. And then on the vertical axis, it's how good it works, typically, what's the experience with it. So most good results have got here on the top to remove nitrogen, for example, nitrate from the soil, but also petroleum hydrocarbons. They're considered relatively easy or feasible. The BTEX, which are aromatic compounds like benzene, for example, some chlorinated solvents because they can be evaporated. But you see also then when you go down, the metals like arsenic and nickel, that takes already something like 10 years to get a visible result. With some other metals, it can take much longer. If you look at uranium, for example, then they talk about, something like 30, 40 years maybe to get some impact. And some of them, like copper and zinc or lead, can take very, very long time. So this is just a general overview of if you have a case like this to consider. This picture may help to see if it's feasible to think about phytoremediation. This is a picture of phytostabilization. It's in a mining site in France. And so the mine was abandoned, and you see here it's a wasteland. So there was no vegetation. And then they applied phytostabilization on it, which means they put vegetation on the lands in combination with some additives like bentonite clay or something that traps the metals to reduce toxicity. And then the plants grow on it and they fix the contamination so that it doesn't blow away with the wind anymore. So it's a type of phytostabilization to control the risk, but it's not really that all the pollution will be gone. Phytoremediation has been applied or studied for explosives. This picture gives an example for TNT or RDX or HMX. So you always have carbon nitrogen compounds, explosives. And it just shows that, yeah, this is the roots, and within the root area, you have a complex mixture of living organisms, each of which can take part in this degradation process because they have certain enzymes that take one pollutant or another one. And eventually you end up, see, with a whole mix of what they call daughter products. So, for example, the TNT, which is three nitro groups, is converted to one nitro group and two amino groups, which may be less harmful, but still may be harmful. It's still a pollutant. And eventually it will turn into something else. So you see from a few starting materials, nitroaromatics, you get a whole bunch of metabolites. So the concentrations of these will go down in the soil, but it doesn't mean your soil is clean. But these reactions can be done and they can help to solve a problem. But be aware that it's a complicated issue that you need, if you do this, you need to analyze in theory all those metabolites as well to make sure that your soil is clean. So it is a solution which is thought of for explosives phytoremediation because it's not very invasive, but it's not that simple as it looks. Good. So that was using plants. It's an on-site technique. The next group of technologies we discuss is in situ remediation technologies. So basically, you tackle the pollution within the soil. And you have two families of techniques that you can use. The first group is based on extracting the contamination from the soil or from the groundwater. The second group is based on destroying the pollutants within the soil by adding some chemicals or bacteria, for example, or stimulating bacteria. So it's extraction versus destruction. And there's for each group quite a number of techniques. So when we look at extraction, what you first have to do is remove the pure product. You saw in one of the earlier lectures, if you have a lot of pollution, then it typically forms a layer that floats on the groundwater, which is a floating layer of petroleum, for example. It's a lot of pollutant mass. You first have to remove that before you start doing something else. What's often done is if pollution is in the groundwater, you just pump up the groundwater and you treat the groundwater. It's called pump and treat. This may be effective for some chemicals, for some others it's not so effective. You can improve it by adding, for example, a solvent or a surfactant to the groundwater to make it more mobile in the soil to pump it up. Some contaminants are volatile. You can remove them by extracting the air from the soil, and then the contaminants that are volatile will be removed that way. The soil vapor extraction. A similar technique is air sparging, in which you generate air bubbles in the groundwater to strip the pollution. And a last technique is a little bit more invasive, is in situ thermal desorption. It's again heating the soil so that the contaminants volatilize and can be extracted. The destructive technologies, the most widely used is chemical oxidation. You infiltrate oxidants in the subsurface that destroy the contaminants. You may apply chemical reduction. It's not done very much, so we don't discuss this in detail. You can apply what's called reactive barriers or reactive zones. That's something between containment and treatments. And we'll discuss later how that works. You stop the contaminant in the barrier, but the groundwater goes through it. So it's not complete isolation, but partially. Bioremediation is often applied in situ, so with bacteria that are stimulated. And sometimes the bacteria that are present in the soil, they can tackle the pollution themselves without stimulating them. And that's called monitored natural attenuation. Important thing is that you show that it works so that your problem will get solved in time. And we'll discuss that also. Before discussing these different techniques, they all are based on properties, the physical properties of contaminants. And I think you saw in the previous lecture that contaminants, when they're in the soil, they can be present either in a dissolved form in the groundwater, they can be absorbed into the soil, they can be volatilized within the soil pores in the soil air. And if they're present in very high concentrations, they can be present as pure products, and that can be a floating liquid of petroleum, for example. Or if it's metals, for example, that can be a metal salt that sticks on the soil. Now, pure product, depending on its density, can be heavier than water or lighter than the groundwater. If it's lighter than the groundwater, it floats on top of the groundwater table. If it's heavier, then it's called dense non-aqueous phase liquid, or DNAPL, then it sinks inside the groundwater until an impermeable layer. And so, as I said, if we try to treat a soil pollution in situ, we always have to start with removing pure products, because otherwise it will keep on dissolving in the groundwater forever. And the situation is, I saw this picture before, I think. So if you have a product that is lighter than groundwater, like petroleum, it will basically make a contaminated groundwater plume close to the groundwater table. Because it's lighter than water, it does not sink too deep, to greater depths. And that's the one that's easier to remove. You see on the right, there's a number of ways of doing it. If the pure product here, the oil layer that you see, is not deep, then you can consider excavating it, which means in the soil you dig a trench, and you can do that every 5 or 10 meters. You dig such a trench, and the oil will collect in the depth of the trench. It will float to the lowest point, and then you pump it up, and eventually the oil is sent to a separation between oil and water, and eventually you have a water treatment to remove then the dissolved oil. So it's the first. So if you have shallow floating product, you can excavate it. If it's deeper, then you cannot excavate it, and then you have to typically make use of wells. So these are pipes that you bring in the soil, typically vertical pipes, which are perforated at the level of the groundwater. And then you bring a pump in those pipes, and there is 2 ways of doing it. There is what we call a 2-phase extraction, which means that you use 2 pumps. One pump is located in the pure product layer, and another pump is below in the groundwater. And this is used, if you pump here, then the groundwater will go down, and you will create this deepest point in the well that the oil by gravity can flow to the lowest point, and it collects here, and you pump it up. So that's a 2-phase extraction. You can also do a multi-phase extraction, which means you pump up the oil together with the groundwater just at one point. Each has its advantages and disadvantages. And also excavation. So if you do the first method of excavating a shallow floating layer, then you have again the risk of emissions, because you have those open collection constructions. Advantages, you can remove a large part of the oil. It's fine if you don't have too many non-volatile components. If you have a lot of volatile components, then you better don't use this technique. The in-situ treatment technique with those extraction wells, if you have the dual pump system, like I said, this one here, the disadvantage of this is the oil layer originally was here at the water table. If you lower the water with this pump, then the oil sinks through the soil before it gets to the well, and it will contaminate it, maybe contaminating this soil, which was not so much contaminated before. So you smear the oil over bigger soil volume, which later on may be difficult to remove. This is not happening so much with this one, because it doesn't lower the water table that much. Disadvantage of this method is you simultaneously collect soil, air, and groundwater and oil. And when it gets above ground, then you typically get an emulsion. It's a mixture of oil bubbles in water, and these emulsions are more difficult to separate and to treat. So each method has its advantages and disadvantages. Now, important to realize is you always have to do this first, but don't hope for 100% removal, because a lot of this oil will stick to the soil, especially if you have heavy oils. They're very sticky, so you probably can only remove a part of it. But you should try to remove as much as you can before applying something else. The other case is removing pure product which has a higher density than the groundwater, and this is typically for chlorinated solvents. And you see the picture on the right. If you have a spill of a chlorinated solvent, because it's denser than water, it will not stop at the water table, the blue line. It will just go down deeper, and it goes down till an impermeable layer, and then it will flow again to another impermeable layer, and eventually it ends up far away from the spill. And so it's very difficult to know where you have to put your pump to pull it up. So the principle is the same. You have here a DNAPL layer above a clay layer. It's a pure product is sitting there. And if you find it, if you know that it's there, you can extract it, for example, with wells under vacuum. But you have to know where it is. That's a tricky thing. So assuming you don't have pure product anymore, then one of the most widely used techniques, especially in the past, is extraction of groundwater. So if you have a contamination that caused a plume of groundwater contamination, so the groundwater flows that way, the spill started here. If you do pump and treat, you start to put an extraction well in the contamination. You pull up the polluted groundwater and you send it to a holding tank, and eventually it's purified, and that way you clean the groundwater. So the principle is basically, you have the picture here on the right. So the soil has pores, holes in it, and the contamination is either adsorbed to the pores, to the soil particles, or it's sitting within it as pure product still sometimes. And you just flush the groundwater, you force the groundwater to flow through it with a pump. So you always attract fresh groundwater from upstream through the contaminated area, and eventually the pollution will dissolve, or it will come from the soil, or will dissolve from the pure product, and it can be extracted above ground and treated. Now, if you do so, then typically what you see is that the concentration time will go down the more product you extract, but it always goes slower and slower. In the beginning, you get very high concentrations, and eventually it takes a lot of time to remove the last. So typically what you do, this is often due to adsorption processes. Whatever is dissolved in the groundwater, you extract it very quickly. But what is adsorbed on the soil, it takes time to desorb from the soil. And sometimes what you do then is that you stop pumping for a while to give time for the pollutants to desorb in the groundwater, and then you pump it again. I think that was a picture that I put in the wrong place. Okay, sorry. Good, so pump and treat, this is what you see. So it all depends on the type of pollutant, how effective and how fast it goes. This is a picture which shows what is the concentration at a certain time after flushing the soil with a number of water volumes, pore volumes. And then you see that it depends on what's called the KD, the dissociation constant of the pollutants. It's a measure for absorption of the polluted soil. So you see that compounds, the yellow line, which strongly adsorb the soil. You really need to flush the soil many times. In this case, you see after 15 pore volumes, you only have removed 20%. While if you do 15 pore volumes of a pollutant, which is absorbing much less to the soil, then most of it will be removed already. So in theory, you can calculate how much time you need to clean a soil with pump and treat with this formula. And this formula, you see the time is dependent on this KD. It's what you see in this picture here. So if you know there's the bulk density of the soil and the KD. So everything depends on the pump volume. The Q is the amount of water you pump per time. And the contaminated volume, the bigger the contaminated volume, the more time. The bigger the flow, the less time. And the important factor is the R factor, the retardation factor, which is determined by the adsorption of the pollutants. Now you have a number of scenarios possible if you apply pump and treat. So typically you see the concentrations decline in time. And this is a picture that shows the time, as time goes on, what is the concentration of the pollutant, and you see it will decline. The ideal case is curve A. So the concentration declines and eventually you end up with clean groundwater if the concentration is below the remediation limit. So this is the remediation goal for the contaminant. But what we see a lot is that you don't reach the remediation target, that the concentration declines, but it stays at a certain plateau. And if you would stop pumping, the concentration will go up again. So you do not reach the goal that the government requires you to clean. And this has all to do with either it's too much adsorbed to the soil, or there is maybe some pure product which keeps on dissolving in the groundwater, and you can keep on pumping for a very long time, and you will not get the target. So this is a disadvantage of pump and treat, and it's very typical when you have compounds that adsorb well or that form pure product. And that's a lot with chemicals like chlorinated solvents. So in order to treat a soil with pump and treat, the soil must be permeable. You need to get the water through it, of course. So if you have too much clay or organic matter, it's not good because it absorbs the pollutants too much and it will take too much time. So it works well, normally well with chemicals which are reasonably soluble in water and do not adsorb too much, like polycyclic aromatic hydrocarbons, forget it, they adsorb too much to the soil. So as I said, pure product can be very bad for the results because it will keep on dissolving and you can pump forever. One thing to keep in mind, if you pump, you typically often lower the groundwater table. And if this happens, if you have buildings standing close to where you pump, as a result of lowering the groundwater table, the soil can start to move and the buildings can get damaged, they can get cracks, and worst case, they collapse. So that's something you always have to think about when you design such a system, that a geotechnical engineer makes sure that you don't have risk that something happens, that you have damage to the buildings. So the groundwater that you extracted from the soil, it has to be purified. Now, this is typically done with a number of water treatment techniques, which are very common, but groundwater is a little bit different from other water. And typically it has a lot of dissolved iron or manganese or carbonate. And so this, when you pump up the groundwater and it enters the treatment plant, then they can start clogging. If you get precipitation of iron or manganese oxides or carbonate, then your system doesn't work so well anymore. So that's different from other wastewater treatment. But you use typically, mostly used is sand filtration to remove iron and manganese so that other things don't clog. And then activated carbon is widely used for organic contaminants. If you have some metal ions, then you use ion exchange resins maybe after the sand filtration. You can also use for rocket fuel, for example. A lot of missiles have perchlorate as propellant gas. You can remove this with ion exchange, for example, or biologically. Also very common is an air stripper. You see it on the picture here. So you see this white tower. That's an air stripper. It's a column filled with a filling material, which is like balls in plastic. And you blow air through it and you get fine bubbles that strip volatile contaminants like benzene or trichloroethene. And you see here the black vessels, that's activated carbon filters. So these are the most common techniques for treating groundwater. All right, so in situ treatment, groundwater extraction is one way to remove contaminants from groundwater. If you have contaminants in the soil zone above the groundwater table, which is the unsaturated zone of the soil, then if they're volatile, then you can remove them with a vacuum. And you create a vacuum in the subsurface by putting those pipes in the contaminated area. So you have the gray area is a contamination. The dotted line shows where the groundwater table typically was. And what you often do is you lower the groundwater table by extracting groundwater, because if you have products which are not so dense as water, like petroleum hydrocarbons, they float on the water, and you have a very highly concentrated area around the groundwater table. So you lower the groundwater by pumping up groundwater with pump and treat, as we saw before. And that way, the whole contaminated area comes in the unsaturated zone, which is where the pores are filled with air. And then you put vertical extraction filters within this contaminated area, and you connect it to a blower that extracts the air. So you get a lower pressure in the subsurface, and the contaminants which are volatile will be taken away with the air that you extract. And the contaminants that are adsorbed to the soil, when they're volatile, they will desorb from the soil. And eventually, all the contaminants are taken away by the airstream. So it's typically applied for volatile contaminants like gasoline, contaminants like aromatics are in there, or alkanes, but also low molecular weight chlorinated solvents like the solvents in the metals industries like trichloroethane or trichloroethane, also often present at military sites because they used to clean metal parts or of weapons or so. Important is, again, like if you flush with water, the soil needs to be permeable. It's the same if you flush with air, the soil needs to be permeable. So not for clay soils. Important is that this unsaturated part of the soil, so distance between the surface of the soil and where the groundwater is, it needs to be big enough so that the extraction filters are not close to the surface of the soil. Because if they're close to the surface, close to the atmosphere, then you will start to suck atmospheric air. And that's a waste of energy, but also that way you get not enough under pressure in the soil and you cannot successfully remove the contamination. So you need to have a soil which is deep enough so that you can install those wells with enough space to the surface of the soil. Important, you have to be careful because often if you have petroleum hydrocarbons that are volatile, they can make explosive mixtures. Especially in the beginning of the treatment, concentrations can be very high. And then when you extract them and they come in the blower that you use to extract the air, if it's not X-proof, then you can get explosions. So it's important to evaluate this at the beginning. You can start doing a pilot test, for example, on a small scale, where you just take one of these extraction filters and you apply the vacuum to it, and then you see what concentrations come, and then you see if it's within the explosive limits or below or above. And then you can take measures, for example, by diluting with air to avoid explosive mixtures. The air that you extract has to be purified, just like the water we saw before. So typically it's with activated carbon filters. If you have a lot of contaminants like petroleum, hydrocarbons, you can incinerate it as well, but then you need high concentrations. So it's a common technique. It's relatively simple to apply, just careful for explosive mixtures. There is another technique which is very similar and often complementary to the soil vapor extraction. It's for treating the groundwater. So there's an alternative for pump and treat. And what you do here is you blow air in the groundwater to generate air bubbles. So you have again here the situation where you have, my mouse is not going well. Okay, so you have the surface of the soil here. You have the groundwater layer. You see the contamination is again typically a petroleum hydrocarbon lighter than other. It sits around the groundwater table. And then you start to install filters under the pollution and you blow air in it. And the air will come out as fine bubbles and they will strip the hydrocarbons or the chlorinated solvents, which are volatile, out of the water. And eventually they come in the unsaturated soil. And so the unsaturated soil, you install again a soil vapor extraction system that removes from the soil whatever you strip from the groundwater. So if you do air sparging, it's always a combination of putting air in the groundwater and extracting the air that you put in the groundwater above the groundwater table with a soil vapor extraction system. The advantage of this system is that it typically works much faster than pump and treat. But it's not always so simple to realize. And the main reason for this is you don't want this situation in the bottom figure. Because if you have here a contamination and you put air below the contamination to strip the contaminants, if above the contaminated area, you have a soil layer which is not so permeable for air, then the air cannot move to the extraction filters above, and you will force the air under this impermeable layer, and it can move 50 meters, 100 meters, 200 meters to the side, and eventually you blow all the pollution to your neighbor, which you don't want. And this is something that happens, in fact, sometimes. So also for this, it's good to do a small test at first with a pilot test with 1 or 2 injection wells and a few extraction wells to see that you can control everything and that you can recover what you mobilize with air. All right, another approach of dealing with contamination in both the unsaturated soil as well as the saturated soil of the saturated soil is that you apply again heat. It's an in situ thermal desorption. So it's similar as what we saw before with excavation. You heat the soil to volatilize certain chemicals which are semi-volatile. And then you mobilize them with heat, and then when they come in the soil air or in the groundwater, then you extract that with extraction filters, and that way you can remove those contaminants with heat. So why do you use heat? There's a number of advantages. The viscosity, the viscosity of oil, for example, it decreases, so they move faster to the extraction point. You increase the water solubility. Organic chemicals are more soluble in warmer water than in cold water. And it's typically a technique which you use for highly contaminated sites with high concentrations, where otherwise it would take too long with the other techniques that we just discussed. So this technique can even tackle pure product. If you have pure product, not if you have a thick floating layer of petroleum, but if you have some droplets of oil or so, it can also tackle it. How you do it? You can heat in different ways. You can do it with steam. You can also apply an electrical current in the soil, like a microwave oven, or you can heat with thermal conduction. And I will just show the principles on the next slides. So the left side of the figure, you see the case of applying electrical currents. So what you do is you have a number of electrodes that you put in the soil, the thin black lines. And within those electrodes, you put an extraction well. It will extract in the unsaturated soil, which is the orange part, that extracts the air, and it extracts the groundwater in the blue part. And so when you apply alternating current to the electrons, between the electrodes, the soil will heat, and eventually heat the soil typically to 80 or 90 or 100 degrees, so not yet just below the boiling point of water. And then the solvents like trichloroethane, they will volatilize and they will move to the extraction well. And then above ground, purify the air and the water. So that's one way of doing it. You can also apply heat in a conductive way, and that's what you see here on the second picture. So in this case, you have a metal pipe that you put in the soil, and this is so this orange, so the red dots are metal pipes. Within the metal pipes, you put again an extraction well, and in this case, those metal pipes, you typically put hot air in it. So you have typically air that's sent through it, and you have a burner with a gas burner above, and it heats the gas again high enough so that you can heat the soil to 80 or 90 degrees. And then again, the same principle, you have a central extraction well. Whatever you mobilize in the air or in the groundwater, you can remove it and purify it above ground. And so third way, as I said, is using steam. It's a little bit more complicated, but sometimes, typically at chemical companies, they have a lot of steam available, and then it can be handy to use the steam that they have already there. And the principle is you have an injection well in the soil. So typically you have here in yellow the contamination in the soil. The blue line is the groundwater table, and the contamination is sitting on a clay layer here. And then the contamination is, of course, started here. So all this area in the unsaturated zone is contaminated, but also in the groundwater is contaminated. And then you put an injection well for steam, and the steam will move into the soil to an extraction well. You put a little bit further a well that extracts the groundwater. And so it will pull the groundwater that you put in, the steam that you put in here will move eventually, as you see on the right side. The whole area will be saturated with steam and will be heated to around 90 or something degrees. You extract the stream, and that way you again evaporate the contamination that you again then extract in the unsaturated soil as well as from the groundwater, like with the other techniques. With this technique, you have to be careful. If you get steam, you get extra condensated water in the groundwater mixed. So you must be sure that the steam will mobilize a lot of contamination, will be very high concentrations of solvent, for example. You must be sure that what you extract here is enough so that the contamination that is mobilized with the steam is not going deeper, because often these solvents are heavier than water. If you do not extract quick enough, they may go down instead of that you extract them. That's a risk with this kind of approaches. All right, so the previous set of techniques were all extraction techniques. You put either vacuum or extract groundwater. So the next techniques are more about destruction. So you inject things within the soil or the groundwater to destroy the pollutants. Yeah. And one of them is in situ chemical oxidation, what they call often ISCO. So the principle is that you destroy organic contaminants with a strong oxidant. There is an example here of tetrachloroethylene. You see in the green molecule here, the C2Cl4. It's a chlorinated solvent. And it's known that it reacts well with potassium permanganate. So permanganate is a purple strong oxidant, or yeah, relatively strong oxidant. It can remove the chlorines, the Cl4 can be liberated eventually with an oxidation product, which is CO2. So this C2Cl4 is converted to CO2, which is harmless except for the climate. And the chlorine is removed as chloride ions. So the compound is not toxic anymore. So it works well for a number of compounds, but not for all. It's difficult to oxidize compounds which are already strongly oxidized themselves. Like PCBs, they have a lot of chlorines already on them, or CCl4, and it's very difficult to remove the chlorines from these. One thing to keep in mind is when you apply chemical oxidant, it not only reacts with the contamination that you want to remove, but it will remove with whatever it sees in its way. Huh? If the permanganate is injected in the soil, it will move with the groundwater. It also reacts with the soil itself. And that's what that consumes a part of the oxidant, which you waste that way because you cannot use it for the contaminant. And that's what you call soil oxidant amount. So you have to realize that you have to add more oxidant to the soil than the contamination, because a part of the oxidant will be lost by reacting with the soil. Also important to realize is that often you do not get complete degradation of the contaminant. So you may get partially oxidized products. They may be harmful themselves, but the problem is that it's difficult to measure them because it's hard to predict which compounds the daughter products will be. And yeah, if you don't measure them, you don't know about it. But it also may be so difficult to measure it that, yeah, mostly it's not applied. So when the typical contractors apply ISCO, then they just measure the compound that they want to remove and they say, okay, it's gone, but they don't care about whatever is there left. So it's something to think about because you really want to solve the problem. There is quite a number of oxidants that you can use to remove pollution. This table shows a number of them which are used often, and it shows some properties that are important. I said permanganate here, this MnO4 is often used, and it has a number of advantages. It's dissolved, it's a salt which you dissolve in water to inject it, and its advantage is it has high stability, which means if you inject it, it can be active for a month, for 2 months maybe, and so it can travel to the groundwater, which is not the case with some other ones. If you have the next one, hydrogen peroxide, it's a very clean reagent because it falls apart with forming water, but it has low stability. Its lifetime is very short, which means it will be there for a week maybe, and then it will be gone. And it's the same, well, for persulfate, it's also used. It's a sulfate salt. It's moderately stable, so it may be there around for a number of weeks. And in general, it's also observed, if you look at this property, is the oxidation potential of an oxidant. It says how strong the oxidant is. The higher the number of the oxidation potential, the stronger the oxidant is, but typically it's reacting very fast and its lifetime is very short. And you see, if you go from top to bottom, the oxidation potential from permanganate is 1.7. You can have much stronger oxidants like per-ozone, which is a mixture of ozone and peroxide, which has an oxidation potential of 2.8. Or often used is Fenton's reagent, which is hydrogen peroxide with an acid added or with an iron salt added to it. It has very high oxidation potential, but it has a very low stability. So in a few seconds, it may be gone, or maybe half an hour, which means if you inject it, it will only have an effect there where you inject it, but it will not travel like permanganate, which will be stable for months. So it's something to realize. This table is something you can use if you have a case where you want to see, if you want to do oxidation, chemical oxidation, which oxidant can I use for which contaminants. So the first column lists the type of oxidants, like in this case, Fenton's reagent, or ozone, or the combination of ozone with peroxide, or permanganate, or persulfate. Persulfate, I didn't show it, it can be also activated, and it's more strongly than the persulfate salt. If you add, for example, iron to it, it becomes a stronger oxidant. And they all have their spectrum of what they can destroy. I'm not going to go over all the table, but it's just to show that you don't have to expect that all these oxidants will destroy everything. So if you have, for example, hydrogen peroxide with iron, it's Fenton's, minimal contaminants of concern, COC is contaminant of concern. That means they can be degraded by this oxidant. And you see, for example, explosives can be degraded by Fenton's reagent in theory. But there's a number of contaminants which are very difficult, like trichloromethane solvents or pesticides. It will not be removed very well. And it's typical for certain oxidants. If you have permanganate, it works very well for some chlorinated solvents like perchloroethylene or trichloroethylene. But for benzene, it does not work so well. And some of them, like PCBs, it will not work at all. So this is just a reference table for yourself. Depending on the contaminant, you can check which oxidant you may use. So some remarks about in situ chemical oxidation. I also already mentioned permanganate. Yeah, it's stable, but it has an inconvenient thing, that character, it is purple. If you inject it, then it moves off-site, and the neighbor has a well to extract groundwater that becomes purple. That may be a problem. And it also can precipitate. When it reacts with an organic contaminant, it forms manganese dioxide, which precipitates on the soil. It may clog certain things. Fenton's reagent, which was a combination of hydrogen peroxide with iron and acid. It's a very strong oxidant which may generate a lot of gas, and those gases may spread from the soil to the surface of the soil, and you may get emissions of volatile components, or you may even get explosive conditions. So be very careful when you apply the very strong oxidants. I said already, the strong oxidants which rely on free radicals have a very short lifespan. So you really have to design your system so that you take this into account, that they don't travel far. Sometimes people think that chemical oxidants can be used for pure product. So if you have a place in a site where the pollution originated, the source zone, and you have a pure layer of product there, let's say a petroleum hydrocarbon floating layer of 10 centimeter thick or 20 centimeter of thickness, do not think that you can remove that with chemical oxidation. These are all chemicals that react when they're in water. They will not react with pure product, and you may even get dangerous conditions. And also something to take care of, many of those chemicals, they're dissolved in water. That means that you get solutions which are heavier than water, than the groundwater. So when you inject them, they may sink to greater depths, and then they may as well take the contamination to greater depths if they don't react with the contamination well. So it's something you have to be careful of. Okay, so I was thinking of using a post now. It's again, it's 10 to 3, so it ends up typically about close to an hour. So I don't know if anybody of you has questions. Otherwise, I would just suggest to do another 10-minute break before the last break. Is there anybody who has a question?
Yeah, I'm looking to the chat. Thank you already, Johan, for this very nice and comprehensive overview of all these techniques. It seems like a lot of those things are very costly and time-consuming. I think that's what they all have in common. I was just wondering, do you have, of course, I know how difficult it is, but an estimation of a cost of, let's say, a relatively moderate contamination? Can you put prices on it? I know it's very difficult, but just an order of magnitude, and of course in West European terms, I would say.
If you excavate the soils and all those you dig a hole, you take the soil out and you move it to the soil recycling center, then most of the soil in Flanders is treated with bioremediation. You treat it in a pile, you put oxygen in it, and that's for petroleum hydrocarbons. Typically, the prices range from around 30 euro per ton, 25 to 30 euro per ton of soil. If you apply soil washing, which is more energy intensive, typically the price would be around 40 euro per ton. If you would apply thermal treatments, then you have to think of prices which are significantly higher, and then they would be typical thermal desorption, I guess 70, 80 to 100 euro per ton, something like that. And so for the in situ, it's more difficult to estimate. But you have to take, if you have small sites where you apply air sparging or something like that, then you start thinking about, let's say, chlorinated solvent site like trichloroethylene from a dry cleaner site. If it's not too big, 50,000 to 100,000 euro for the cleaning up of the site. If the site becomes bigger, then you may think of a few 100,000 euros. So that's the ballpark. And then we don't talk about big companies. If you have a metal factory which is contaminated over hectares, that's going to be very costly.
No, okay, just some numbers, but just to put it in perspective. Thank you, Johan. I see that Nathan also has a question.
Yeah, for sure. I guess in the situation of Ukraine, specifically with agricultural soils that are, sufficiently contaminated with things like heavy metals or explosives or hydrocarbons, what type of remediation strategies would make the most sense for a situation like that?
It's a very good question. That's a problem we have in Belgium also, because a lot of these techniques, they change the state of the soil, which is not good for agriculture. And the most logical approach would be the phytoremediation, but you've seen the limits of phytoremediation. We have this problem in Flanders now where we have a lot of PFAS contamination in agricultural land, and then they look indeed at phytoremediation as the only viable solution, because if you can excavate it, but if you excavate it, you lose the agricultural land, and then you have to replace it by soil which is typically not agricultural soil. So that's the disadvantage. And so I can imagine you can use this for craters of bombs that fall within an agricultural area, and that you have a crater of, let's say, that you have a truck of soil that you have to move, then you can move that to a soil recycling center. That would be the most logical solution. If you have a more diffuse pollution of a hectare of few hectares or tens of hectares of agricultural land, that's not a viable solution. And then, so it depends on what the pollution is. Say if you have metals, heavy metals, for example, if it's, either they're metal particles, then they can't do much. Then you have to excavate it again, but typically not so dangerous. But if it's a dissolved metal from metal particles or whatever, then besides phytoremediation, you could do stabilization, which means you add adsorbing compounds like zeolites or something like that. They can be often waste products also from industry. and you mix it in the soil, and that will fix the metal so that the plants will not take it up anymore. So you may think of solutions like that. And there may be some, you may have organoclays, which may be used for organic contaminants. So you could blend some binding materials within the soil that can immobilize the contaminants so that they're not taken up by the plants. That would be the logical way, I guess, if phytoremediation is not feasible because it takes too long. Because the excavation, yeah, it's for large areas too costly.
Thanks.
Yeah. Okay. Thank you, Johan. Yeah, it's always good to remind the situation and indeed what is feasible or what could be some solutions.
Yeah,
in that
but of
field.
course, like many of these techniques, I guess you don't, in the situation of Ukraine, you don't have to think only of wide areas of agricultural land. I can imagine if you have a tank that's destroyed, you have a lot of oil spill, which is very local, and then you come in the area of those techniques which I showed you, and then you may have to dig a hole and remove the oil from the soil and ship it with a ship or some to a recycling center. If the same thing, you have a plane that came down, it may be very localized effect. So there will be a lot of war damage. You don't only have to think of the wide areas of agricultural land. Even within agricultural land, you will have hotspots that you may need the more intensive techniques for. If you have a truck with just have diesel, but you have gasoline, and then you can apply air sparging on this small spot. They don't have to be so complicated. In the United States, you typically think about big air sparging systems, which are very costly, but you can apply them on a relatively small scale, not too costly. But it all depends on the situation.
Yeah.
Mm-hmm.
Okay, thank you. I think that's clear, Johan. Indeed, let's have a break. So we see each other at 3 o'clock Belgian time, 4 o'clock Ukrainian time. So this will give us the moment to have some rest and to have a drink.
Okay.
Okay, thank you, Johan.
Good.
See you.
See you.
Okay, I think we can resume for the last part of this afternoon session. I hope everybody had a drink and could fuel again some energy. Also, Johan, may I remind you on the speed of you're
Yeah,
speaking.
okay.
You are doing very well, but I know how difficult it is.
Yes, I know.
To keep on track. So, but just a kind reminder.
Yes, I'll try.
No problem. Okay, Johan. So please go ahead for the last part.
Yeah. Okay. So the last part starts with in situ bioremediation techniques. So you use bacteria that you stimulate in situ to degrade pollutants. And there is a number of groups of bacteria that can apply such reactions. We first talk about aerobic bioremediation. And when you use oxygen, so bacteria that use oxygen, they apply aerobic bioremediation. You can realize this with a number of methods like bioventing, which is similar to soil vapor extraction as we discussed before. You have biosparging, where you blow air bubbles in groundwater to oxygenate the soil. You can apply biostripping, where you put a compost layer on top of the soil in combination with air sparging or biosparging. And you can infiltrate oxygen or other chemicals that release oxygen in the groundwater. So these are all oxidative reactions with oxygen. Bacteria can also apply degradation reactions without oxygen present, and we talk about anaerobic bioremediation. And it can be either microbial oxidation or microbial chemical reduction. So we'll discuss these in detail in the next slides. Last class of biological approaches is natural attenuation. That means you let nature do its job. The bacteria that are present within the soil, they will degrade the contamination itself without helping them. But that's something you have to monitor very carefully. So the first approach would be the in situ bioremediation by oxidation with contaminants. So you can either inject oxygen in the groundwater. You just put a vertical pipe, for example, in the groundwater, perforate it, and you infiltrate oxygen. But you can also do this in an anaerobic manner by adding other oxidants, which are, for example, nitrate or sulfate. They carry oxygen, and in the groundwater, the bacteria will take the oxygen out of it as natural oxidants. So another class of reaction is, like I said, reduction of contaminants, and then you inject what's called a carbon source or an organic substrate. It's an organic molecule such as lactic acid or molasses, which is a waste product from the sugar industry. It's a sugar, or what's called here HRC. It's a commercial product, hydrogen release compound, or vegetable oils, which are emulsified. Now, all these compounds, they have in common that they have carbon-hydrogen bonds. And so bacteria can take the hydrogen out of them to replace, for example, chlorine with hydrogen to make a compound that's less harmful. So it's often used for removal of chlorinated solvents. CH stands for chlorinated aliphatic hydrocarbons, molecules like trichloroethene. So there you can remove the chlorine atoms by those bacteria. That's dechlorination. You can also apply these reductive reactions to remove dissolved metals in groundwater. And there you don't really remove them. You remove them from the groundwater and you precipitate them on the soil. It's called bioprecipitation. And we'll show what it's based on later. Sometimes you inject nutrients to keep the bacteria happy, but that's rarely used. Sometimes bacteria are not there enough, or they're not very happy. You can add extra bacteria to help the reaction going on. And that's called bio-augmentation. So chemical principles that it's based on is, so if you have microbial oxidation by oxidation reactions, the bacteria either use oxygen, and then you get, for example, a molecule like toluene. Bacteria break it down with oxygen to CO2, which is harmless, and water. If oxygen is not present, bacteria can sometimes use nitrate or manganese dioxide, which is present in the soil, as manganese minerals or iron minerals, or they can use sulfate in the groundwater, which is dissolved, or finally also CO2, for which they will make methane. So these are all, electron accepts what they call it, but it's basically natural oxidants that bacteria can use, and they all generate from this contaminant CO2 and some reaction products. Now, in this column, it lists delta G stands for the change in free energy that bacteria get from this reaction. So this reaction releases energy, and the bacteria use that energy to grow. You see for the first line with oxygen, the energy is larger than the last line where you get methane from CO2. Bacteria here get 20 times more energy for this reaction with this one molecule of toluene than they get with oxygen. So for that reason, bacteria will first use oxygen in the environment. And if oxygen is all consumed or is not there, then only they start with nitrates, because they also get a lot of energy from nitrate. They may use manganese dioxide, which is itself converted in manganese ions. So eventually they go down here, but it's a sequential step typically. So they always prefer oxygen, like I said, and if it's not available, they turn to the other ones. Sulfate is very common in groundwater, so they often use sulfate if oxygen is depleted. So realize that, they grow faster than oxygen and they will have a preference for it. So if they use oxygen, how do you supply it to make them happy? So you can apply oxygen in groundwater, for example, to degrade pollutants like benzene, toluene, ethylbenzene, xylene, mineral oil, gasoline, kerosene from planes, vinyl chloride, which is a degradation product from TCE, etc. So bacteria can degrade them by making CO2, and most commonly use air. Air has 20% oxygen and 80% nitrogen, so it's the cheapest way. The limitation of air is you can dissolve only 10 milligrams of oxygen per liter. So it's a limited amount that you can dissolve in the groundwater. For that reason, sometimes people use technical oxygen, but it's expensive. With technical pure oxygen, you can, of course, dissolve 5 times as much. But you can, there's companies that sold this kind of equipment. It's a hollow fiber membrane. You put oxygen in it and it dissolves without bubbles the oxygen in the groundwater, and they make a bioscreen, for example, but it's rarely used because it's expensive. You can also use hydrogen peroxide. It's a common chemical. It's a bulk chemical. It will release oxygen, and it can dissolve more, let's say 100 milligrams per liter rather than 10 times more. Or some companies sell this product. It's a magnesium compound, magnesium peroxide, which releases oxygen in the soil. And it's sold as a long-term release of oxygen. If you just put air in the groundwater, the oxygen doesn't live long. This is a product, it's a slurry, it's a solid product that's injected in a slurry, and it will generate oxygen for a few months, probably. So you can treat the soil for a long time with this compound, but it also comes with a cost. And the final one is percarbonate. It's in your laundry detergent. It's not sodium percarbonate. This is the wrong formula here. It should be percarbonate, which is the hydrogen peroxide attached to it. But anyway, it's also a way of supplying oxygen. So all of these, again, the soil needs to be able to flush with a solution that contains the oxygen. So the soil needs to be permeable, except for the ORC, which you can inject as a slurry. There is some more common and cheaper ways to get oxygen in the groundwater or in the soil for the bacteria. And it's with the techniques that we showed beforehand, soil vapor extraction and air sparging. If you do it to stimulate bioremediation, it has a different name, but it's the same technique. So bioventing, you use a soil vapor extraction system. But in this case, it's not for volatile compounds like before. You don't want to remove with vacuum the volatile compounds. It's also for compounds that are not volatile, like diesel oil or any type of petroleum hydrocarbon that's not volatile. You, in this case, use the system not to extract the contaminant, but to suck oxygen through the air. So if you apply a vacuum here from the air, you will get oxygen inside, and bacteria will use oxygen to degrade the petroleum hydrocarbons, for example. But that's for the unsaturated zone above the groundwater. If the pollution is in the groundwater, then you can apply the air sparging technique. You inject the oxygen under the pollution in the groundwater. In this case, the air, inject air, and the air bubbles will supply oxygen, which becomes dissolved in the contaminated area where the bacteria again degrade the contaminants. The difference with soil vapor extraction and air sparging is that you don't need so much flow of air because you just need enough to supply oxygen to the bacteria, which often means that you don't need the air purification system that comes along with it. So it's a much cheaper way of doing it than with soil vapor extraction. So these are the most common ways if you want to supply oxygen to the subsurface. So it's biofending for the unsaturated zone and air sparging for the saturated zone. Another type of microbial transformation is not an oxidation reaction, but a chemical reduction reaction. And it's often used for chlorinated solvents, things like trichloroethene and trichloroethane. So you see the chemical reactions sequence here for the case of perchloroethene. Perchloroethene has 4 chlorine atoms on an ethene molecule. And what bacteria can do is they can strip off in step by step one chlorine at a time. So you go from 4 chlorines, you replace one with hydrogen, you have 3 chlorines left, which is trichloroethylene. Then they remove a second chlorine replaced by hydrogen. And eventually, if you do that 4 times, you end up with a compound that doesn't have chlorine anymore. It's called ethene, which is an innocent compound. It's not harmful. So it's a stepwise chemical reduction that the bacteria do. Now, you have to supply the bacteria with the hydrogen to replace the chlorine. And that's what you do by adding an organic substrate to the groundwater, which is a chemical reductant basically for the bacteria. So if you add the most common substrates are molasses, which is sugar, or lactate or vegetable oil. I think I mentioned them before. So what the bacteria do with them in the subsurface, they ferment those simple molecules and eventually they get an equivalent of hydrogen gas. Basically, it's a reduced form of hydrogen, which they use then to replace chlorine by hydrogen. So that's the basic principle. Now, there is a wide variety of organic molecules that you can use, and they have their advantages and disadvantages, but there is, you can group them. You have simple organic molecules. They were used originally the most, and these are typically sugars like molasses or neutralase, which is from the potato industry. It's a sugar from the potato industry, or lactate from the cheese industry, for example, or acetate or glycerol. These are simple molecules. They all release hydrogen and can be used for this. They're simple molecules, which means they're metabolized very fast by the bacteria, so you have a quick result. But as they're metabolized fast, they disappear fast also. So you have to repeat them. You have to repeat the injection, which is a manipulation that costs money. Because they're small molecules, they're well soluble in water, so it's easy to spread them across the contaminated volume. The fact that they disappear relatively quickly, that you have to inject them frequently, led to the fact that some companies started supplying larger molecules and they live longer, so they're more stable in the subsurface. Now we think of vegetable oils, which are typically emulsified because an oil you cannot dissolve in the groundwater, or a polymer of lactate, so larger versions of the previous class. So they will react way slower. They will sustain longer in the subsurface, so you don't need to inject them so frequently. But because they're not so soluble in the groundwater, it's more complicated to spread them in the subsurface. And because each of these has its advantages and disadvantages, more recently they started to mix those two to have the best of both worlds. So you have a mixture of small molecules and big molecules to have a long enough effect while you still have a quick start of this remediation. Now, it's a microbial conversion of chlorinated solvents, and especially for this type of reaction is one big risk. Because not all microbes can do this reaction. And if you see this reaction scheme, you go from 4 chlorines to 3 chlorines, the TCE. Then you should go from 2 chlorines through 1 chloride, which is vinyl chloride. And eventually you have ethene, which is innocent. They use to ripe bananas in the ships coming from South America. But the problem is this needs a special strain. So the first step here can be done by many bacteria. But this step here, taking it from TCE over vinyl chloride to ethene, only a few bacteria can do this, and they're not everywhere available. And so if you don't realize this and you start stimulating bacteria, what you end up with is a big accumulation of this compound here, or maybe this compound, but you don't get the non-toxic compound. So that's a risk of this this type of contamination. Especially risk because this compound moves faster to the groundwater. It's a smaller, more soluble molecule, and it's much more toxic than what you start with, which is already very toxic. So you make the problem bigger than it was before. So how do you protect yourself of doing that? You can check the presence of these bacteria with certain DNA techniques, which is called qPCR. They can, if you send the sample of the groundwater to the lab, they can check, is this bacteria there? If it's not there, then you shouldn't do this. If the groundwater already has ethene before you start remediating, then you know that the bacteria are probably there because it already formed by natural attenuation, the harmless product. Okay. So that was for chlorinated solvents. You can use microbial chemical reduction also for metals. Now, metals cannot be biodegraded, but you can reduce or diminish their mobility in the groundwater, and therefore they will not flow away with the groundwater and do not pose a risk for neighbors or drinking water wells that are nearby. And in this case, the principle based on the fact that bacteria, they can use sulfate, which is present in the groundwater very commonly, and they reduce the sulfate as an alternative for oxygen. They reduce the sulfate when they are supplied again with a sugar or some other carbon source. So the carbon source will be used to reduce the sulfate, and the sulfate, you see it in the reaction below. So you have an organic substrate reacts with sulfate, and you form from the sulfate sulfide. And sulfide has a property to make very insoluble metal sulfide complexes. So the metal which was first present in the groundwater in a soluble form becomes insoluble and it precipitates on the soil. And therefore it's not mobile anymore, and you don't have a groundwater pollution anymore. So it's what's called bioprecipitation. So it's for metals definitely cheaper than applying pump and treat, which can take a very long time. But it's a microbial reaction, which is a little bit more complicated to realize than applying pump and treat. Anaerobic remediation can also be applied for a number of contaminants, which may also be relevant for the Ukraine situation. For example, you have nitrate. The nitrate can be converted by bacteria to nitrogen gas, which is harmless. You know, nitrate, especially in agriculture areas, it's typically present, maybe also in explosive mixtures. Sulfate, like I said, reduced to sulfide for trapping metals. Perchlorate may be a relevant one. Perchlorate, it's a rocket propellant. And we have experience at Vito. We applied it for a site in France to remove perchlorate from the groundwater just by applying a carbon source like this. And it's an effective technology. TNT can be reduced by microbes because you convert NO2 groups to amino groups. Again, you may end up with metabolites which are still not harmless, but it's a technology that can be used. And also for RDX, similar also nitric compounds that bacteria can reduce and therefore make less harmful. It's observed when you have nitrate and perchlorate together with RDX, then the bacteria are not so effective anymore. So sometimes those compounds, when they're present together, they may be negative for the degradation that otherwise would be possible if they're not together as a mixture. But so we saw the basic principles of how bacteria can be stimulated, or how you can inject oxygens in the soil. But how do you do that? You need to get the reagent that you need to where you need it in the contamination. If you do in situ, it means within the soil. So if you want to inject reagents, you can do it in different ways. The simple ways is you make a solution of the reagent, a dilution of 1 or 5 or 10%, and then you inject it in groundwater with a vertical well that you put in the ground. You see a picture on the right where you see at the surface of the soil that you have a pipe going in the ground, and you just have here the valve to opening, to control the supply of liquid. So it's a solution you make. The advantage of using a vertical well to get the solution down is that it's simple, it can be done by gravity, and you can do it multiple times. So once you install the well, you can come back after 3 months and after 1 year and after 3 years, and you just pump in a new solution. You can do it just by gravity, or you can pump it if the soil is not so permeable. You have to realize what you pump in the soil will not spread homogeneously. It typically follows more permeable soil areas, which means you may not reach all the pollution. That's something we have to be aware of. And to control where whatever you infiltrate goes in the subsurface, you can combine injection through an infiltration well, and you put somewhere else wells that extract the groundwater, and then you can direct what you inject to where you want it to be. So it's a technique that you especially apply in well-drained soils. You can easily inject a solution that will move through the soil to supply bacteria, for example, with reagents. An alternative is that you apply what's called direct push injections, and that's a higher pressure inject techniques where you don't put a well, but you have a drilling machine here on the bottom, as you see, and so you have a metal rod that's hollow, which has a tip, a cone at the tip and an opening, and then you inject at a certain depth with the metal pipe that you drill in the soil to a certain depth. You can go easily to 10 meters, 15 meters. You pump a slurry of the reagent you want to inject with this injection system deeper in the soil. Advantage of this is you can also do this in not so permeable soils, think about loamy soils or so. But the problem is that, it's a one-off shot, which means if you have to do this again 3 months later or 6 months later because the reagent is used all, then you have to mobilize your drilling equipment again, which is a costly approach. So it's more reserved for soils which are not so permeable. Also here, distribution in the subsurface is maybe more complicated even, because with those high pressure systems, you often have preferential flow paths that they follow the most permeable soil layers. All right, so far we have seen active remediation technologies for really manipulate the subsurface with chemicals or bacteria. You can also let nature do its job, and that's called natural attenuation. So the EPA, US EPA defines as natural processes within the soil and groundwater, active without human intervention, to reduce the mass and the toxicity and the mobility and the volume or concentration of pollutants. So the bacteria present in the soil will execute one of these processes because the conditions are relatively favorable by nature. And so what you should see is with time is this picture here. So you have the original situation. You have a source of pollution. It has it's spilled in the soil and the groundwater, and the groundwater will take the pollution. It will dissolve in it, and the groundwater that moves away from the source will create a pollution plume. And you will see that this plume will always grow bigger until some point that it will not grow bigger anymore. It's stable. And with time, when bacteria, for example, start to degrade these pollutants, then it will be shrinking again. It will become smaller, and eventually the plume will be kind of exhausted. You will see very low concentration. So that's the ideal situation. And monitored natural attenuation means that you monitor this process by measuring in the field to demonstrate that this happens, that the plume does not get bigger, but it gets smaller and eventually disappears. So it's based typically on biodegradation, bacteria that degrade contaminants, but it can also be chemical degradation. Some chemicals, they just split in water because of hydrolysis. But soil components, soil components are chemically reactive themselves, some soil minerals, so they can also degrade contaminants. So these are the active natural attenuation mechanisms which you want to be dominant. Other processes may reduce the concentrations in the groundwater. Precipitations of metals, like we showed before, can happen. The question is, will this happen for a long time, or will they dissolve again with time? And then you have the phenomena which always occur. If a pollutant is in the groundwater, it will absorb to the soil, and it will get lower concentration because it disperses in a bigger volume, so it will be diluted. And eventually, some volatile ones may evaporate, and that will lead to a decline in concentrations. But all the ones in red are not the ones that should be dominant, because there you don't solve the problem. The pollutant mass remains the same. You really want to have that mass of pollutant goes down, and that's by degradation reactions. And that's something you have to show to accept this technology. So monitor natural elevation, you can call it a technology because you apply monitoring. And so you have to do monitoring in the field, take samples and analyze in the lab. And so what you want to demonstrate, the most important part is that the concentrations decline, and they do not decline at one point, but they decline all in the plume or in the source. So you have to measure in time so that you can establish a trend line. So you have to see the concentrations will go down, and this has to continue. And then eventually from those trend lines, if you extrapolate them, you can say, okay, within so many years, my problem will be solved. So that's the most important one. And you also have to make sure that your plume doesn't get bigger, of course. So you monitor that it's not growing bigger. Another what's called second line of evidence is what's shown in the figure here. So as we've seen before, bacteria can use natural occurring oxidants to catalyze degradation of pollutants. And that means that you get consumption of those natural oxidants. And so that results in a plume picture like this. So we said before that oxygen is always used first by bacteria, which means if you get in the highly contaminated area where the pollution is the oldest, all the oxygen will be gone, and also the nitrate will be gone, and the sulfate will be gone. So the green color means that you have metagenic bacteria which get the least energy out of the pollution. They persist there. And if you go further down the plume, then you will see traces of sulfate and iron and nitrates remaining. And eventually you get in the white zone where you still have oxygen that you can measure. So if you can establish this pattern going from close to the source, that you see that you have a change in all those electron acceptors or oxidants. If you see this pattern, that's a secondary proof that bacteria are there that break down the pollutants. So it's what the EPA calls the second line of evidence. So it's also something you have to measure and show. A little bit more complicated or expensive is, but typically relevant for chlorinated solvents. You have to show that bacteria that are needed are present. Remember that some reactions, they stop halfway. So you can measure the bacteria by PCR methods that measure DNA to show that the bacteria are there. Should also at least consider when you evaluate this that you have enough oxidants from natural sources present. So if the contamination is very high, you need a lot of sulfate, a lot of nitrates, a lot of iron. So try to make this balance. Is there enough sulfate present to degrade all those pollutant loads?
Johan, if I just may interrupt for a question. When you say you need to measure all these components and also the microcosm and the bacteria, is this always done in the groundwater? So basically you collect the groundwater?
Yes. This is typically for groundwater because you see the plume develop in the groundwater. Natural attenuation, this methodology doesn't apply to the unsaturated soil because you cannot apply all these methods there. So but the only thing you can do basically is measure the concentration over time of the pollutants. But it's typically for plumes which develop and which migrate off-site, which are a threat to the surroundings that you apply this.
Yeah, and then you have on the one hand the chemical parameters, then the bacteria. So it means that you can, if you pump up the groundwater, you can get an idea of the bacteria present by using what you mentioned, the PCR techniques.
Yes, indeed. You just sample groundwater, you ship it to a lab that does qPCR. That's typically some universities do this, but also in Flanders or in Holland, commercial labs do this as well.
Yeah. So this means that for performing this natural attenuation, you mostly also include a bacteria test to see what is present. Of course, maybe depending on the contaminant that you want to follow.
Right. Depending on the contaminant, because I said petroleum, hydrocarbons, bacteria are always there. For the metals, always, almost. But not for chlorinated solvents. So if you have chlorinated solvents, and then I'll show you on the next pictures, sometimes if you start your baseline measuring campaign, if you see that ethene is already formed, then you know that the bacteria are there by nature. But if you see from PCE and TCE only DCE and nothing from ethene, yeah, then you know that the bacteria may be lacking, and then you may take a sample of groundwater to analyze for the bacteria.
Yeah, okay, that answers the question. Please, I was advised once again to ask you to speak as slow as possible, Johan. I know it's very difficult for you. But no, thank you so much.
Okay, if I have still some time left, yeah, okay, yeah. All right, good. So, and then the ultimate proof, if you really want, you can show in the lab also that the bacteria are there or that the degradation occurs by doing lab tests. So what you typically do is you take a sample of the soil under the groundwater table and a sample of groundwater, and you ship it to the lab without exposure to oxygen, and then the bacteria that are present will do their reactions, and it's easy to measure them in the lab. You can develop those timelines in a few months, and that's 100% proof that it will be effective. But it's more complicated and more expensive. So normally you apply the first 2 lines of evidence: concentration decline over time, plume stays stable, and measure the natural oxidants, because it's easy to do. Now, how do you measure or monitor natural attenuation? There's a very simple scheme of a plume. So you have the source here in the groundwater. The groundwater generates a plume in time, and you have to show that this plume is stable, and eventually that declines. So first you measure before the plume in the non-contaminated area. It's upwards from the source area. Why do you do this? Yeah, it's a reference point. And you also measure in that the natural oxidants which are necessary for the degradation. So the concentration of oxygen, of sulfate or nitrate. So it's a double reason why you do this. It's your reference point. And then, of course, you measure in the contamination, and you do this in the central flow path of the plume. And then you go a different distance from the source. There you should see the concentrations decline. So here you're close to the source, you have then high concentration of contaminants, it declines. But here you have also probably very low concentration of oxygen, while here, more towards the end, not all the oxidants have been consumed, and you will still see the oxygen. So that's why you need several of those monitoring points along the flow path. And then you also put ones besides around the edges where the water is still clean, because you want to make sure that with time it doesn't get bigger. And that way you can see easily or quickly that there is a problem that's growing bigger, which you don't want. And eventually you still have at the very end, you have what you call some sentinel wells or alarm points. That imagine that you have the property boundary here, or a drinking water well, or a factory that extracts groundwater. You really don't want your plume to move there. So that's a kind of a point of no return. Once you see that the pollution arrives there, or that you see a change in the degradation products arriving there, then it's time to look for another solution. Then you stop this approach and you start pumping or something else. So that's basically the principle of monitoring natural attenuation. And this is what, typical picture for natural attenuation. You will see some plumes, bacteria have a harder time to deal with them. And as typical, this is reflected by plume length. So it's a study in Germany under the CORA project, where they looked at a number of plumes. You see 15 plumes of BTEX and 9 plumes of other hydrocarbons. And so then they looked at the plume lengths what the typical length is. So you have a maximum plume length for chlorinated solvents of 4,400, which is the same as the 90th percentile, and the median plume length of 1.5 kilometer in this case. And so you see that these lengths are much larger than the pHs, which absorb stronger, or the petroleum hydrocarbons, which degrade faster, and the BTECs, which are a little bit more difficult, which are more mobile and travel faster than the other hydrocarbons. So, but it's also a result of natural attenuation. If bacteria have a more difficult time with chlorinated solvents, the plumes will get bigger. And this shows the picture for chlorinated solvent. It's the field survey they did in the Netherlands a while ago. So they looked for a big number of sites, and then they see at how many sites do you have a problem with degradation products where the reaction stops. And remember, you want to go all the way to here. You do not want to stop it at VC, vinyl chloride, which is very toxic. And then complete degradation is the blue. You see only in 22 of the sites they had complete degradation. While they had, with the VC, something fell off here, but a significant number of sites has vinyl chlorides has endpoints, and a lot of sites have this where the reaction stops halfway. So in 40% of the cases, they see that there is no bacteria that take it all the way. So if you would just rely on natural attenuation for this chlorinated solvent and say, okay, it will dissolve by itself, and many times it will not. It just shows that it's not always that easy. Oops. All right. So that brings me to the end of the part of active remediation measures to control the pollution by removal or destruction. And so sometimes, it's too complicated. The solution is too deep, or it's too big, or whatever, or you don't have the money available or the resources at this time, so you want to contain the contamination. And so the goal is that you prevent the contamination to spread from the source area to somewhere where it poses a risk for economic activities or humans. And there is a number of ways you can do that. The first is what's called a geohydrological isolation, containment, which just means that you pump the groundwater so that groundwater cannot pass a certain point. I'll show you on a slide next how it works, but basically pump so that the groundwater stays in its place and doesn't move off-site. More drastic way is engineered constructions. So to encapsulate, you would just want to enclose the contamination. With impermeable constructions, they can be vertical, horizontal. So you make an enclosure which is permanent and it's invasive. And then you have a solution between containment and active remediation, which is called permeable reactive barriers. These are barriers where the groundwater flows through, but the reagents are present in the barrier that degrade the pollutions or trap the pollutions. A little bit more detail about each of them. So geohydrological methods is basically that you protect the downstream sensitive receptors. So for example, you have here in this area a drinking water company that's extracting groundwater, and the contamination goes that way. So what you can do here is at the end of the contamination, just drill a number of wells. You extract the groundwater here, and that makes sure that way the pollution doesn't go further. There's nothing that's happening to this end. So this will keep on going forever for the next 10 or 20 or 50 years. But you at least make sure that it doesn't go further. That's the geohydrological measure of containment. It's only typically a temporary solution before you can do something definite, because it costs a lot to purify the groundwater. So you cannot do this forever. So if you think it's going to go on forever and you cannot remove it, then you can really encapsulate it. So with engineered physical barriers. So this can be horizontal or vertical. Horizontal can be on the soil surface. So you see the picture on the right, typically use some plastic foils, HDPE, for example, and that way you can limit exposure of people to the contaminated soil, but you also limit evaporation of, for example, volatile contaminants. you can do it with a lot of things. So you can do it with this kind of foils in plastic, but you can also do it with asphalt, for example. You can make a parking lot above your contaminated area, and it's also isolated, or a concrete parking lot, for example. You can add clay mats as mean of containment. And what's more and more used for large surface areas, if the contaminants are not volatile, you can just remove the first 50 or 70 centimeters of soil that you move to another site to clean. And then the rest of the contaminated soil, you put a clean layer of soil on top of it. And that will prevent exposure of people to the contamination. And this we do typically in Belgium for large contaminated areas where there is not, you don't have really volatile contaminants. A little bit more exotic, but it's feasible if you have a contamination which may be deep or not. You can also, if you cannot excavate it, you can inject substances like clays or bentonite clays under the contamination. And if you do this close to enough that they overlap, you can make a whole seal, and you can combine it with vertical insulation so that, you can also contain the contamination. You can put vertical barriers. There is many ways how you can do this. Just a few examples. So a vertical barrier typically means that you, around the contaminated area, you make sure that it cannot get away by some, engineered barrier. This is a steel plate barrier. It's relatively simple to install, but it doesn't go so deep, typically 10 meters. It's just steel plates, and the plates are hammered, as you see on the right side. You have a machine with a weight on it that hammers the steel plates down. The risk is that, if you have a big stone, that they start to bend, but it's not very common. So it's a conventional way. They also used a lot for construction engineering. And these plates you see, they're not flat, but these are elements that you hook up into each other with locks, what they call. And it's important when you hammer them down that the locks stay intact, because otherwise the groundwater that has to be isolated will flow through the metal wall. So that's one of the risks. But it's common applied technology. Now these barriers, you have to, if you have a floating product like petroleum, then it will hang around the groundwater table. It will not go very deep. And then the barriers do not have to be very deep. They just have to be well below the contamination. If you have products that go deep, like chlorinated solvents, and then you have to make the barrier all the way to a clay layer, so that, because pollution will sink up to the depth of the clay layer. And it can be sometimes quite deep, and you cannot realize it with this approach. Another approach may be this. It's like a spiral excavator that you can pull up the soil and replace the soil by a hardening mixture of bentonite, clay, and cement, for example. We used a lot in geoengineering for constructing buildings, so you get those piles of hardened material. And that way you can just also do this completely around the contamination to seal it and contain it. All right, so there's many other ones, but it goes too far to discuss them all. Another way of containing pollution is what's called a permeable reactive barrier. And why do you do this? What I didn't mention in the previous one, if you make a physical barrier around the pollution and under the pollution, then there will always be water that comes within this containment, typically from rain that falls over the surface and maybe some leaks. And it means you always have to keep the water level in the containment lower than the surroundings, so that if there is leaks, that it doesn't leak to the environment. But that means you need to pump some groundwater and treat it, which costs a lot of money. And for that reason, they developed a while ago permeable reactive barriers. It's also a containment where you don't have this issue that you pump groundwater, so you have the contamination here. It makes the plume, and if you want to stop it, for example, at the border of the property, then you make a trench in the soil. You dig out some soil of, let's say, 0.5 meter up to the impermeable layer of the clay layer, for example, and you fill this trench with a reactive material. It's a material that reacts with the contamination in the groundwater, so it either absorbs it or it destroys it. And because this is a granular reactive material, like maybe metal particles or carbonate particles, the groundwater will flow through it. you don't have this need for pumping up groundwater before the containment, and so the water that comes out is clean, and all the contamination is taken care of in the barrier. So there's a concept of reactive barrier. How do they make them? Here's some pictures on the right. If it's not too deep, up to 10 meters, you can use those big digging machines or saws. They typically use them already for construction if they want to make trenches for whatever, drainages or so. But they can use them for installing this type of barrier. So you can go up to 10 meters deep. You see it working on the picture on the bottom. So it's a big chain, like a chainsaw, but a very big one. So it pulls up the soil, and when the trench opens, when the soil comes up, you have, in this case, a big bag with reactive material that you drop in the trench, and eventually you fill up the whole trench with something that removes the pollutants. So what do you put in the trench as reactive material? It can be an adsorbent, like activated carbon, which absorbs, for example, benzene. You can manipulate the pH. If you have heavy metals in the groundwater, you cannot, for example, carbonate cobbles. They will increase the pH. You can stimulate bacteria to do biodegradation, and then you can apply wood chips or mulch as an organic substrate. Or you can apply zero-valent iron. This has been done on a wide scale in the past, because zero-valent iron, you see the picture, this is a waste product from the metal industry. So it's iron waste, little particles of iron. But iron is chemically reactive as a reducing agent. So it also can generate hydrogen when it comes in contact with water. So basically you have these metal particles, the iron will eventually be oxidized, and it will generate hydrogen. And again, the hydrogen on the reduced form can be used, well, the iron will catalyze the reaction of dechlorination like we saw before with bacteria. So you will replace chlorine atoms with hydrogen, and eventually you get ethene. So it's the same principle, but now a chemical, not a biological reaction. And this is a metal that, if you install a metal trench, it will go on for years and years to generate hydrogen to take care of the contaminants. Now, the limitation of those barriers that you dig in trenches is that they only go up to 10 meters depth. If you need deeper measures, then you can apply the principle by what's called reactive zones. So it's again shown here. You have a contaminant plume, you have the source, you have the big plume that develops, the groundwater goes downwards. So if you have, for example, the property boundary here and you don't want it to go further, then you can install injection wells like we saw before. They can go deep if you want to, and you inject reagents to destroy the contaminants. So you have many options. You stimulate bacteria with biosparging, with oxygen. You can release chemical oxidants like permanganate. They have slow release versions of it that generally relieves it, that dissolves it over a long period. So you can go deeper, and it's cheaper than a reactive barrier, but it's more difficult to control because with the trench, everything has to go to the trench. Here again, you may not be sure that you get a good distribution, and you always probably have to come back every so many months or years to inject again. Right. Okay, so that wraps up what I wanted to share with you about remediation technologies. So I hope that it was clear and relevant for you. And so thanks for your attention. If you have some more questions, I try to answer them.
Yeah. Okay. Thank you very much, Johan. I think although I know it's a science on its own, to have a full view on it, I think you touched the different topics. So that was really nice to see what is all available in the sense of remediation techniques, ex situ, in situ, chemical point of view as well. So I think it's highly relevant. And of course, as we said previously as well, it is a case by case depending on the scale, the money you have, the problem. So, but yes, therefore, it was good to have the general overview of all the techniques that are currently involved.
Thanks. Yeah, I put it in the chat here in the green below. You see, there's much more detail, of course, of how you engineer this and what are the pitfalls. So for each of the techniques, you can have many pages or even many reports of 100 pages of how to apply them. And you can find many of them on the website of the US EPA, which you should see below. It's cluein.org. It's a very good website. But all the techniques I mentioned, you find documents and references of case studies. But it's too much to bring all the details in such a medicine. Yeah, it's meant as an overview of what's available.
Yeah. No, I don't see any more questions in the chat, but also as in the previous sessions, all people can still ask questions afterwards to us or to send them to Anna to compile them, and we will be happy to answer them or give your expert opinion on that, Johan. Having said this, I think it is time to close this session. And then it was one of the last general sessions we had foreseen. I think there will be only one more next week on groundwater sampling. But from tomorrow on, we will continue with the analytical sessions. So tomorrow there will be a large session on analytical techniques related to the determination of nutrients in soil, and also to some physical soil parameters. So that's it for tomorrow. But by now, Johan, thank you once again for this really nice presentation. And thank you all of you for listening this afternoon. And then we see each other tomorrow. I think it will be at 9 o'clock our time and 10 o'clock your time. Thank you, and see you tomorrow.